The ocean covers 70% of the surface of this planet. It is the single largest feature of the world we live on, stretching from pole to pole, filling every basin and trench the Earth has carved over billions of years. And yet, as of mid-2024, only about 26% of the seafloor had been mapped using modern high-resolution technology. That number comes from the Seabed 2030 project, a global effort to chart the entire ocean floor before the end of this decade. They are not even close. Nearly 3/4 of the ground beneath the waves remains, for all practical purposes, invisible to us. We have sharper, more detailed maps of the surface of Mars than we do of the terrain sitting beneath the water on our own planet. And in the spaces between what we know and what we do not, there are stories. Stories that have been passed between sailors for centuries. Stories that modern science has tried to explain and sometimes failed. Ghost ships found drifting in open water without a single soul aboard. Sounds rising from the deep so loud they were recorded by instruments thousands of miles apart. Structures sitting on the seafloor that looked like they were built by human hands in an age when no human should have been building anything. Entire vessels, some of them among the largest of their era, that sailed into clear weather and were never heard from again. In the hours ahead, we are going to sink into those stories one by one. Some of them are centuries old, wrapped in myth and retelling until the facts are hard to separate from the legend. Others are recent, surfacing only in the last few years, backed by satellite imagery and deep-sea cameras. A few have been partially explained by modern science, though even those explanations leave questions hanging in the water like sediment that never quite settles. And some of them remain completely, stubbornly unanswered, locked away in the deepest and most inaccessible places on Earth. So settle in, let the current carry you, and if you find yourself here every week for these deep dives into the unknown, make sure you are subscribed so you never miss one. Let us begin where every good maritime mystery should, with a ghost ship. On the morning of November 7th, 1872, a two-masted sailing vessel called the Mary Celeste slipped her moorings at Pier 50 on the East River in New York City. She was a brigantine, a compact but sturdy type of merchant ship about 103 feet long, rigged for transatlantic crossings with a combination of square and fore and aft sails. Her hull had recently been refitted and reinforced. Her deck was clean. Her cargo hold was loaded to capacity with 1,701 barrels of denatured industrial alcohol, a toxic substance used in manufacturing, bound for the port of Genoa, Italy. The voyage was expected to take roughly 3 to 4 weeks, depending on weather and wind. Aboard were 10 people. Captain Benjamin Spooner Briggs, a 37-year-old New Englander from a long line of seafaring men, was in command. Briggs had been sailing since boyhood. His father had been a ship captain. His brothers had gone to sea. By 1872, he had achieved a high standing in his profession and was known among his peers as a competent, cautious and deeply religious man who did not drink alcohol. He had taken command of the Mary Celeste after purchasing a share of the vessel, and he had handpicked every member of the crew for this voyage with care. His wife, Sarah Elizabeth Briggs, accompanied him, as was common for captains' wives in that era. Their 2-year-old daughter, Sophia Matilda, was also aboard. Their older son, 7-year-old Arthur, had been left at home in Massachusetts in the care of his grandmother so he could attend school. The crew consisted of 7 men. First mate Albert G. Richardson, a seasoned sailor who had served under Briggs before and was married to a niece of the ship's co-owner. Second mate Andrew Gilling, a New Yorker of Danish descent, about 25 years old. And 4 general seamen, all Germans from the Frisian Islands, brothers Volkert and Bos Lorentzen, along with Arian Martins and Gottlieb Gutschall. A later testimonial described them as peaceable and first-class sailors. In a letter to his mother written just days before departure, Briggs declared himself satisfied with both ship and crew. Sarah Briggs wrote to her own mother with similar optimism, noting that the men appeared quietly capable and that she hoped they would continue as they had begun. There was no sign of trouble. No tension among the crew, no anxiety about the ship or the journey ahead. On that Tuesday morning the Mary Celeste moved out of the East River and into New York Harbor, passing through the Narrows and into the open Atlantic. The weather was cold but manageable. The ship settled into her heading east by southeast and began the long crossing. For the first 2.5 weeks, the Mary Celeste sailed into deteriorating weather. The Atlantic in the November is never kind, and the ship battled rough seas and strong headwinds as she pushed toward Europe. But she was making progress. The last entry in the ship's daily log was recorded at 5 o'clock in the morning on November the 25th, 1872. It noted the ship's position as roughly 6 nautical miles from the island of Santa Maria, one of the easternmost islands in the Azores, a small volcanic archipelago sitting about 900 miles west of Portugal. That was the last anyone ever heard from the Mary Celeste. 10 days passed with no further communication. No signals, no sightings, nothing. Then on the afternoon of December 5th, 1872, the crew of a British merchant vessel called the Dei Gratia spotted a ship in the distance, moving erratically through the choppy Atlantic about 400 miles east of the Azores. The ship appeared to be under partial sail, but was yawing strangely, as though no one was steering her. Captain David Morehouse of the Dei Gratia had a personal connection to the vessel. He had dined with Benjamin Briggs in New York just before both ships departed for Europe. The Dei Gratia had left New York 8 days after the Mary Celeste and had been following a slightly different route. When Morehouse realized the drifting ship was the Mary Celeste, he knew something was wrong. She should have arrived in Genoa weeks ago. Morehouse sent a boarding party of 3 men across the water. What they found has haunted the history of the sea ever since. The Mary Celeste was completely deserted. There was not a single person aboard. The ship's only lifeboat was missing. One of the 2 water pumps had been disassembled. Roughly 3.5 feet of water sat in the cargo hold, an amount that was notable but nowhere near enough to threaten the ship or justify abandonment. The hull was intact. The sails were set but slightly damaged, some furled improperly, others torn. Below decks, the cargo of 1,701 barrels of alcohol was still in place, though later investigation would reveal that 9 of the barrels were empty. Curiously, those 9 empty barrels were the only ones made of red oak rather than white oak, suggesting their construction may have allowed the volatile contents to leak. The crew's personal belongings were undisturbed. Clothing hung in the quarters, razors sat by bunks, pipes for smoking rested where they had been left. A 6-month supply of food and water remained aboard, untouched. The ship's chronometer and sextant were missing, suggesting whoever left had taken navigational instruments, but the ship's clock was still running and the compass was damaged, found lying on the deck rather than mounted in its binnacle. The ship's charts had been scattered below decks, and the main halyard, a sturdy rope about 3 inches in circumference used to raise and lower sails, was found broken and hanging over the side of the vessel. There was no blood, no sign of violence, no evidence of fire or explosion, no scorch marks, no gunshot damage, no indication of collision with another vessel. The Mary Celeste was, in nearly every measurable way, seaworthy. She could have sailed to Genoa, and yet every person aboard had left. The men from the Dei Gratia, now seriously undermanned because Morehouse had split his small crew between the 2 ships, sailed the Mary Celeste the remaining 800 miles to Gibraltar. It took them several difficult days. The ship arrived on December 13th, and she was immediately impounded by the British Vice Admiralty Court for salvage proceedings. What followed was one of the most exhaustive maritime investigations of the 19th century, and one of the most frustrating. The court's officers, led by the Attorney General of Gibraltar, Frederick Solly Flood, examined every inch of the ship. They tested stains found on the captain's sword and on a railing, initially suspecting blood, but chemical analysis proved they were not. They considered the possibility that the Dei Gratia's crew had murdered the people aboard the Mary Celeste in order to claim salvage rewards, but found no evidence to support this. They explored the idea that the crew had gotten into the alcohol cargo and gone on a drunken rampage, but the alcohol was denatured, meaning it had been deliberately rendered poisonous and undrinkable for exactly this reason. Flood was convinced there had been foul play. He said so publicly, but he could not prove it, and the investigation produced no definitive answers. The salvage court eventually awarded the Dei Gratia's crew a payment for rescuing the ship, but the amount was unusually small, about 1/5 of the Mary Celeste's value, as if the court wanted to express suspicion it could not substantiate. Benjamin Briggs, Sarah, little Sophia, and the 7 crew members were never seen again. Not a single body was recovered, not a piece of clothing, not a fragment of the lifeboat. The Atlantic swallowed them completely. In the decades that followed, the mystery of the Mary Celeste became one of the most enduring puzzles in maritime history. Arthur Conan Doyle, years before he created Sherlock Holmes, published a short story in 1884 called J. Habakkuk Jeffson's Statement, based loosely on the case but filled with invented details and a fictional survivor. The story was so convincing that many readers believed it was a factual account, and it revived public interest in the mystery at a time when it might otherwise have faded. Theories multiplied. Some suggested a waterspout, a tornado over water, had struck the ship and terrified the crew into abandoning her. Others proposed that submarine earthquakes, which can produce violent shaking and strange sounds in the water, had convinced Briggs that the ship was breaking apart. The alcohol fume theory gained significant traction. In this scenario, the 9 leaking barrels of red oak had released volatile fumes into the hold. When the hatch was opened, the fumes may have rushed upward with enough force to blow the hatch cover off, creating a brief but terrifying blast that Briggs could have interpreted as the beginning of an explosion. In a panic, he might have ordered everyone into the lifeboat to wait at a safe distance while the fumes dissipated. Supporting this theory is the physical evidence. The hatch cover was found upside down on the deck when the boarding party arrived, consistent with having been blown off from below, and the broken main halyard, found hanging over the side, could have been used to tie the lifeboat to the ship, allowing the crew to trail behind at a safe distance. If a storm then rose and the halyard snapped, the lifeboat would have been cast adrift with no way to return to the Mary Celeste. In an open lifeboat in the North Atlantic in late November, survival would have been measured in hours, not days. A more recent theory, explored in a 2007 documentary produced with input from oceanographer Phil Richardson of the Woods Hole Oceanographic Institution, suggested that a faulty chronometer may have given Briggs an incorrect reading of his position, combined with the partial pump disassembly, which may have prevented accurate measurement of how much water was in the hold, and rough November seas that were sloshing water around and making everything seem worse than it was. Briggs may have genuinely believed his ship was sinking near land and ordered an evacuation. The log's last entry placed the ship within sight of the Azores after all. If Briggs thought he was closer to shore than he actually was, he may have expected to row to safety, but the Mary Celeste, without anyone to steer her, drifted 400 miles in 10 days before the Dei Gratia found her. The lifeboat and its passengers would have been left far behind, alone on the open ocean. None of these explanations has ever been confirmed. The Mary Celeste continued to sail under new owners for another 12 years, but she was considered cursed by many sailors and changed hands frequently. Her end came in January 1885, when her last captain, Gilman Parker, deliberately sailed her into Rocheleau Reef off the coast of Haiti as part of an insurance fraud scheme. Parker had loaded the ship with a worthless cargo and insured it at inflated value, planning to wreck the ship and collect the payout. Authorities uncovered the plot. Parker was charged but died before he could be tried. The Mary Celeste, already shattered on the reef, was left where she lay, slowly breaking apart in the Caribbean surf. In 2001, novelist and adventurer Clive Cussler claimed to have located the wreck of the Mary Celeste off Haiti, but later analysis of the timbers retrieved from the site showed the wood had still been part of a living tree at least a decade after the Mary Celeste sank, meaning the wreck belonged to a different ship. And so the original mystery endures. 10 people left New York on a clear November morning aboard a sound ship with a full cargo and 6 months of supplies. Somewhere in the North Atlantic, they abandoned that ship and were never seen again. The ocean took them and kept them, and in a century and a half, it has offered not a single clue as to why. It is the ghost ship that started them all, and the water that hid its answer has never given it back. And while the Mary Celeste drifted without her crew in the eastern Atlantic, hundreds of miles to the southwest, an entire region of ocean was building a reputation for something far worse. Not a single ghost ship, but a graveyard of them. The Bermuda Triangle sits between 3 points on the map. Miami, Florida to the west, San Juan, Puerto Rico to the south, and the island of Bermuda to the north. The region covers roughly 500,000 square miles of open Atlantic, a vast stretch of deep water crisscrossed by shipping lanes, air traffic corridors, and the warm, powerful currents of the Gulf Stream. For more than a century, it has been associated with the unexplained disappearance of vessels and aircraft, and while many of those disappearances have perfectly rational explanations involving storms, human error or mechanical failure, a handful of them remain genuinely unsolved. Among those, one towers above the rest as perhaps the single most baffling maritime loss in American naval history. The USS Cyclops was a Proteus-class collier, a type of naval support ship designed to carry coal and supplies to warships at sea. She was built by William Cramp and Sons in Philadelphia, launched on May 7, 1910, and commissioned into the United States Navy on November 7th of that year. She was not a small vessel. The Cyclops displaced nearly 20,000 tons, fully loaded, stretched 542 feet from bow to stern, and was 65 feet wide. At the time, the trade journal International Marine Engineering described her as the largest naval collier in the world. Her cargo holds could carry over 12,500 tons of coal, and she was equipped with massive cranes and rigging systems for the grueling, dangerous work of transferring fuel to warships at sea. For the first several years of her career, the Cyclops served in a peacetime role, fueling battleships and cruisers along the Atlantic seaboard and in the Caribbean. When the United States entered World War I in April 1917, the Cyclops was pressed into wartime service and assigned to the Naval Overseas Transportation Service. In June 1917, she joined the convoy escort for the 1st American Expeditionary Force sailing to Saint-Nazaire for France. She carried fuel, supplies, and members of Army Base Hospital No. 18, the first hospital unit to arrive in France. After returning to the East Coast, she continued her coal and cargo missions through the summer and fall. On January 8, 1918, the Cyclops departed the Navy Yard in Norfolk, Virginia, loaded to her marks with coal, mail, and miscellaneous stores bound for the South American patrol fleet operating off the coast of Brazil. The day was cold and overcast, with light snow falling. The harbour had been frozen over, and Liberty parties from anchored ships had walked across the ice that morning. As the Cyclops ploughed through ice floes in the ship channel, she narrowly avoided a collision with another vessel, the USS Survey, which was outbound for the Mediterranean. It was the first of what one survivor would later call the untoward incidents that dogged the ship on her final voyage. The Cyclops was commanded by Lieutenant Commander George Worley, a man who would become as much a part of the mystery as the ship itself. Worley was born in Germany as Johann Friedrich Weichmann. He had jumped ship off the coast of San Francisco in 1878 and assumed the identity of a friend, living under the name George Worley for the rest of his life. He was an eccentric, gruff officer of the old school, known for carrying a cane and for a command style that veered between erratic and authoritarian. He berated his crew openly. He overruled his navigator's corrections. On the voyage south, he sailed past the entrance to the harbour at Bahia, Brazil, by 48 miles before realizing the error and turning around. His officers protested his decisions and were brushed aside. One crew member, who later left the ship, described the atmosphere aboard as a toxic command climate. The Cyclops delivered her coal in Brazilian waters and prepared for the return voyage, but instead of heading home with empty holds, she was ordered to take on a new cargo. Approximately 10,800 long tons of manganese ore, a dense metallic mineral used in the production of steel and munitions, was loaded aboard. The United States had entered the war, and demand for raw materials was enormous. Manganese ore is significantly heavier than coal, and the Cyclops had been designed to carry coal, not ore. The difference in weight distribution and the way the cargo would behave in rough seas would become a focal point of later theories about what went wrong. The ship departed Brazil in mid-February. During the return voyage, the starboard engine failed. Worley reported that repairs could not be made at sea and would need to wait until the ship reached Baltimore. Running on one engine, the Cyclops could make only about 10 knots, roughly 2/3 of her top speed. On March 3rd or 4th, the ship made an unscheduled stop in Bridgetown, Barbados, where Worley went briefly ashore. The Cyclops took on additional supplies and then departed on the afternoon of March 4th, 1918, heading north toward Baltimore. She was expected to arrive on or around March 13th. She never made it. No distress signal was ever transmitted. No one aboard responded to radio calls from the hundreds of American ships operating in the western Atlantic. The lifeboats were never lowered. No wreckage was found floating on the surface. No oil slick. No bodies, no life preservers, no debris of any kind. The disappearance was not made public for more than a month. The Navy had initially hoped the ship had simply been delayed or had put into an unscheduled port for repairs. When it became clear that the Cyclops was not coming back, the information was released to the Associated Press in April. The reaction was immediate and intense. French and American vessels searched the trade routes between Barbados and Baltimore. They found nothing. Rumours and theories spread through the press like wildfire. Sabotage by the German-born captain. Capture at sea by the enemy. A German submarine torpedo. A mutiny that spiralled out of control. The German Navy denied any involvement, both during and after the war. No German submarine had reported engaging the Cyclops, and no evidence of a torpedo attack was ever found. A violent storm swept through the Virginia Capes area around March 10th, and some believed this might explain the loss, but the Cyclops was a large and well-constructed ship, and storms alone seemed insufficient to destroy her so completely that not a single piece of wreckage remained on the surface. Secretary of the Navy Josephus Daniels addressed the loss in his annual report for 1918. He wrote that there had been no more baffling mystery in the annals of the Navy than the disappearance of the USS Cyclops. That assessment has never been revised. On June 1st, 1918, Assistant Secretary of the Navy Franklin D. Roosevelt officially declared the Cyclops lost and all hands deceased. A total of 306 people were gone. 15 officers, 221 enlisted men, 6 naval officer passengers, 64 enlisted passengers, 2 Marines, and the United States Consul General at Rio de Janeiro, who had been travelling home aboard the ship. To this day, the wreck of the USS Cyclops has not been found. Searches ceased long ago without success. Her loss remains the largest non-combat loss of life in United States Navy history on a single steel vessel, and in a detail that deepens the mystery to an almost unbearable degree. 2 of the Cyclops' sister ships also vanished under nearly identical circumstances. The USS Proteus and the USS Nereus, both former naval colliers that had been sold to civilian operators, disappeared in the same general area of the Atlantic during World War II. Both were carrying heavy loads of metallic ore, similar to the cargo aboard the Cyclops during her final voyage. Neither ship sent a distress signal. Neither was ever found. Rear Admiral George Van Deurs, who had studied the Cyclops-class ships extensively, suggested that the design of these vessels, contained a fatal flaw. The I-beams that ran the length of the hull could erode when exposed to certain types of corrosive cargo, weakening the ship's structural integrity over time. This degradation had been observed on the USS Jason, another ship of the same class, and was believed to have contributed to the sinking of a similar freighter called the Chuki, which snapped in two in calm seas. If the Cyclops' hull had been weakened by years of carrying corrosive loads, the addition of nearly 11,000 tons of dense ore, combined with rough seas and a single functioning engine, could have created a catastrophic structural failure, a sudden breaking of the hull that would have sent the ship to the bottom so fast there was no time for a distress call. It is the most accepted theory among naval historians, but it does not explain the total absence of wreckage. When a ship breaks apart at sea, the debris field is enormous. Fuel oil spreads across the surface in a slick that can stretch for miles. Wooden fittings, life preservers, and personal effects float for days or weeks. Bodies, grim as it sounds, rise to the surface. The Cyclops left none of these things behind. The Atlantic closed over her as though she had never existed. And the Cyclops was not the only vessel to vanish in the waters of the Bermuda Triangle without explanation. On December 5th, 1945, 5 TBM Avenger torpedo bombers took off from the Naval Air Station at Fort Lauderdale, Florida, on a routine overwater training exercise designated Flight 19. The flight was led by Lieutenant Charles Taylor, an experienced combat pilot who had flown Avengers in the Pacific during World War II. The 4 other planes were piloted by qualified aviators, several of them students on a final training flight. In total, 14 men were airborne. The exercise was straightforward. Fly east over the Atlantic, conduct practice bombing runs on a small shoal called Hens and Chickens, then continue on a triangular course that would bring them back to Fort Lauderdale. The weather was clear. Visibility was good. There was no reason to expect trouble. About 90 minutes into the flight, Taylor radioed the base to report that both of his compasses had malfunctioned and that he could not determine his position. He believed they had strayed over the Florida Keys, far to the south of their intended course. Ground controllers attempted to guide the flight back using radio bearings, but communications were intermittent and plagued by static. Over the next 2 hours the situation deteriorated. Taylor appeared confused and contradicted himself on the radio, at one point believing they were over the Gulf of Mexico, then changing his mind. The other pilots in the flight were heard asking Taylor which direction they should fly, and his answers were inconsistent. As fuel ran critically low, the last radio transmissions from Flight 19 were garbled and faint, then silence. All 5 aircraft and all 14 men disappeared. A massive search operation was launched immediately. Among the search aircraft was a PBM Mariner flying boat carrying 13 crew members. The Mariner was known to have a persistent fuel leak, a condition so common among that aircraft type that crews sometimes called them flying gas tanks. The Mariner also vanished. A merchant ship in the area reported seeing a fireball in the sky and passing through an oil slick around the time the Mariner would have been airborne, strongly suggesting the aircraft exploded in flight. But no wreckage from the Mariner was recovered, and no wreckage from any of the 5 Avengers of Flight 19 has ever been found. The disappearance of Flight 19 became the most famous incident associated with the Bermuda Triangle, and it remains one of the most heavily investigated aviation mysteries in history. The most likely explanation, supported by the available radio transcripts and weather data, is that Taylor became disoriented when his compasses failed and led his flight progressively farther out over the Atlantic instead of back toward land. By the time the pilots realized how far they had gone, they were too low on fuel to make it back. All 5 aircraft likely ditched in the ocean after running dry, and the crews, even those who survived the water landing, would have quickly succumbed to exposure in the open Atlantic in December. But the total absence of wreckage remains difficult to explain. Avenger torpedo bombers were large, sturdy aircraft. 5 of them going down in a relatively confined area should have produced a recoverable debris field. The ocean floor in the search area is not extraordinarily deep, and yet in the 8 decades since Flight 19 vanished, not a single piece of any of the 5 aircraft has been identified. Researchers have pointed out, fairly, that the Bermuda Triangle is one of the most heavily travelled shipping and aviation corridors on Earth, and that statistically, the number of incidents in the region is not disproportionate to other areas of comparable traffic. The United States Coast Guard does not recognize the Bermuda Triangle as a uniquely dangerous zone. Many of the disappearances attributed to the area occurred during storms, in darkness, or under conditions where human error was a contributing factor. Theories about the triangle range from the plausible to the exotic. Methane gas deposits on the seafloor could theoretically erupt in massive releases that would reduce the density of the water above them, causing any ship in the area to lose buoyancy and sink in seconds. Rogue waves, once dismissed as sailors' tales, are now documented phenomena, some exceeding 100 feet in height, capable of overwhelming even large vessels. Compass anomalies, possibly caused by local variations in Earth's magnetic field, could contribute to navigational errors, and the Gulf Stream, one of the most powerful ocean currents on the planet, runs directly through the triangle and is capable of rapidly dispersing wreckage over hundreds of miles, making recovery almost impossible. None of these explanations, alone or in combination, fully accounts for every incident. And the Cyclops, sitting somewhere on the floor of the Western Atlantic, with 306 souls, remains the most stubborn case of all. Every few years someone announces a new search effort, improved sonar technology, better understanding of currents and drift patterns, and advances in deep water exploration give each new attempt a slightly better chance than the last. So far the ocean has not cooperated. If the Atlantic can swallow a 542-foot warship and leave nothing behind, the Pacific Ocean has its own way of keeping secrets, not with disappearances, but with sounds. Sounds so powerful and so strange that when scientists first recorded them, they had no framework for understanding what they were hearing. In the summer of 1997, a network of underwater microphones positioned across the floor of the Pacific Ocean picked up something that nobody could explain. The microphones, called hydrophones, were part of an autonomous listening array operated by the National Oceanic and Atmospheric Administration, NOAA, based at the agency's Pacific Marine Environmental Laboratory in Newport, Oregon. The system had been designed to monitor undersea earthquakes, volcanic activity, and the movements and migrations of marine mammals, but its origins were far older and far more secretive than that. The hydrophone array was built to augment a much larger network called the Sound Surveillance System, or SOSUS, which the United States Navy had installed across the ocean floor during the Cold War to track the movements of Soviet submarines. By the late 1990s, the military applications had largely wound down, and the equipment had been repurposed for scientific research. The hydrophone sat at strategic depths in what oceanographers call the SOFAR channel, a layer of water at roughly 1,000 meters deep, where temperature and pressure conditions cause sound to travel extraordinary distances with minimal loss of energy. A sound generated in the SOFAR channel can travel literally thousands of miles before it fades. That summer, the Pacific Array captured a signal unlike anything in its extensive catalogue of known ocean sounds. It was ultra-low frequency, sitting at the very bottom of the range of human hearing, and it was staggeringly loud. The signal was detected simultaneously by hydrophones positioned more than 3,000 miles apart, which meant whatever had produced it had generated a truly enormous amount of acoustic energy. When researchers at NOAA's Pacific Marine Environmental Laboratory first analysed the recording, they noticed that the sound rose rapidly in frequency over the course of about 60 seconds, a pattern that looked, on a spectrogram, remarkably similar to the vocalizations of a living creature. It had the shape of a biological call, the frequency sweep of a whale or a very large marine animal. They called it the bloop. The name was informal, almost playful, but the implications were not. If the sound was biological, it had been produced by something far larger than any animal known to science. The blue whale, the largest creature ever to have lived on Earth, is the loudest known animal, capable of producing calls that can be detected hundreds of miles away. But the bloop was several times louder than a blue whale's call. Whatever had made it, if it was alive, would have to be incomprehensibly massive. The source of the sound was triangulated to a remote point in the South Pacific Ocean at approximately 50 degrees south latitude and 100 degrees west longitude. That location sits in one of the most desolate stretches of water on the planet, far from any landmass, deep in the Southern Ocean west of the tip of South America. By coincidence, or perhaps not, the coordinates are very close to Point Nemo, the oceanic pole of inaccessibility, the single point on Earth's surface that is farthest from any land in every direction. It is also, as fans of horror fiction were quick to note, close to the fictional location of R'lyeh, the sunken city described in H.P. Lovecraft's stories as the resting place of the slumbering cosmic entity Cthulhu. The internet, predictably, had a field day with that coincidence, but for the scientists at NOAA, the question was serious. Christopher Fox, the chief scientist of the agency's acoustics program, was among the first to study the recording. In an interview with CNN in 2001, Fox stated that he believed the bloop was likely caused by ice calving in Antarctica, but in a later interview with the science journal New Scientist in 2002, he offered a more nuanced view. Fox said that while the audio profile of the bloop resembled that of a living creature more than anything else in their database, its sheer power made a biological origin difficult to accept. He described it as the most likely of the unidentified sounds to come from some sort of animal, but acknowledged that no known creature could produce a sound of that magnitude. For the next 15 years, the bloop remained one of the most tantalizing mysteries in ocean science. It was not the only strange sound NOAA had recorded. The agency's hydrophone arrays had captured several other unidentified signals over the years, each given its own evocative name. Julia, a sound recorded on March 1st, 1999, lasting about 2 minutes and 43 seconds, was attributed to a large iceberg running aground off Antarctica. The slow down, detected in May 1997, was a sound that gradually decreased in frequency over about 7 minutes. The upsweep, first detected in August 1991 when the Pacific Array began operation, was a long train of narrow band sounds that appeared to be seasonal, peaking in spring and autumn, and the train, recorded in March 1997, produced a steady rising tone that sounded eerily like a locomotive heard from a great distance. Most of these sounds were eventually attributed to ice activity in the Southern Ocean, and in the end so was the bloop. Between 2005 and 2010, NOAA deployed additional hydrophones closer to Antarctica to study the acoustics of ice movement. Researchers conducted extensive surveys in the Bransfield Strait and Drake Passage, two notoriously turbulent stretches of water between South America and the Antarctic Peninsula. What they found was that ice cracking and fracturing was the dominant source of natural sound in the region, and that some of those sounds, particularly those produced by massive ice quakes, had spectrograms that were nearly identical to the bloop. In 2012, NOAA officially updated its assessment. The bloop, the agency concluded, was consistent with noises generated by cryoseisms, which is the technical term for the fracturing and movement of large masses of glacial ice. The confirmation came in part from tracking a specific iceberg, designated at A53A, as it broke apart near South Georgia Island in early 2008. The sounds produced by that disintegration matched the bloop's acoustic signature with remarkable precision. Oceanographer Robert Dziak, who led much of the analysis, later explained that the public perception of the bloop as an animal sound was largely a result of how the recording was typically played back. The files that circulated online were almost always sped up by a factor of 16, which compressed the 60-second signal into a few seconds and raised its frequency from infrasound into the audible range. At that speed, it did indeed sound like a creature's roar, wet and guttural and alive. But when played in real time, Jack said, it sounded much more like what it was: thunder from below the waterline, an icequake, the death rattle of a glacier. The mystery, scientifically speaking, was solved, but the bloop never quite lost its grip on the imagination. The idea that something vast and unknown might be producing sounds in the deepest, most unreachable parts of the ocean is a thought that, once planted, is difficult to uproot. 95% of the ocean remains unexplored. The Hadal Zone, the deepest layer below 6,000 meters, is one of the least investigated environments on Earth. Entire ecosystems thrive in those pressures and temperatures that would kill any surface creature instantly. If there are things down there we have not yet found, and there certainly are, it is not unreasonable to wonder whether some of them might be large enough, strange enough, and loud enough to produce sounds we cannot yet explain. The bloop was ice, but the question it asked, what else might be making noise in the deep, remains unanswered. And if the sounds of the deep Pacific kept scientists guessing, for nearly 2 decades, the seafloor off the coast of Japan has posed a visual mystery that has been debated for even longer. In 1986, a Japanese scuba diver named Kiichiro Aratake was exploring the waters off the southern coast of Yonaguni Island, the westernmost point of Japan's Ryukyu island chain, located roughly 100 kilometers east of Taiwan. Aratake was scouting dive locations, particularly drawn to the area by the large populations of hammerhead sharks that migrate through the region every winter. The water was clear, the current was strong, and as Aratake descended along the rocky seafloor, he saw something that stopped him in his tracks. Rising from the seabed was a massive rectangular formation that looked from every angle like a man-made structure. It had flat surfaces, sharp right angles, and what appeared to be a series of wide regular steps carved into its face, rising from a depth of about 25 meters to within 5 meters of the surface. The formation was enormous, roughly 100 meters long, 60 meters wide, and 25 meters tall. Its edges were clean, its proportions were symmetrical, and sitting on the ocean floor, surrounded by the rounded, weathered boulders typical of the region, it looked completely out of place. Aratake reported his discovery, and within months, researchers began descending to study what quickly became known as the Yonaguni Monument. The site drew immediate attention from both the scientific community and the public, and it has been the subject of fierce debate ever since. The most prominent advocate for the monument's artificial origin is Masaki Kimura, a marine geologist at the University of the Ryukyus in Okinawa. Kimura has studied the site for more than 2 decades, returning to the water dozens of times to measure, map, and photograph the formation in exhaustive detail. He is convinced that the Yonaguni Monument is a man-made stepped monolith, a structure built by human hands and later submerged by rising sea levels or tectonic activity. Kimura initially estimated the formation to be at least 10,000 years old, dating it to a period when the site would have been above water. He later revised this estimate to 2,000 to 3,000 years ago, arguing that tectonic activity had pushed it below sea level after construction. He claims to have identified not just a pyramid, but the remains of castles, roads, monuments, and even a stadium spread across the underwater site. If Kimura is right, the implications are enormous. A 10,000-year-old structure off the coast of Japan would predate the pyramids of Egypt by thousands of years and would suggest the existence of a sophisticated civilization in the Pacific that has been entirely lost to history. Kimura has connected the monument to the legend of Mu, a mythical lost continent in the Pacific, and to the Jomon people, a prehistoric culture that inhabited the Japanese archipelago from roughly 14,000 BC to 300 BC, and who were among the first people on Earth to develop pottery. But Kimura's claims have been met with significant skepticism. The most prominent critic is Robert Schoch, a geologist at Boston University, who has visited and studied the site extensively. Schoch argues that the Yonaguni monument is entirely natural, formed by well-understood geological processes acting on the local sandstone and mudstone bedrock. He points out that the rock in the area contains numerous well-defined parallel bedding planes, horizontal layers along which the stone naturally splits into flat surfaces. The rock is also crisscrossed by sets of parallel vertical joints, natural fractures that produce the sharp right angles and rectangular shapes that make the formation look artificial. Yonaguni Island sits in one of the most seismically active regions on Earth. Earthquakes, which are frequent and powerful in this part of the Pacific Ring of Fire, tend to fracture rock in regular geometric patterns. Schoch has stated flatly that he knew the formation was not artificial from the moment he first saw it underwater. He argues that many of the photographs of the site are carefully angled to make the lines look more regular than they actually are, and that features Kimura identifies as carvings of animals or faces as simply natural scratches and erosion patterns, the kind of shapes the human eye instinctively tries to organize into recognizable forms, a phenomenon psychologists call pareidolia. In 2019, a team of researchers led by Takayuki Ogata conducted a topographical analysis of Yonaguni Island, using digital elevation models and geological field investigations. They examined outcrops at 3 locations on the island's surface and concluded that the underwater monument's features were consistent with natural weathering and erosion of the local bedrock. They noted that similar formations, complete with flat surfaces, sharp angles and stepped profiles, could be found at other locations along the south coast of Yonaguni Island, above the waterline, where no one would claim human construction. Neither the Japanese Agency for Cultural Affairs nor the government of Okinawa Prefecture has recognized the Yonaguni monument as a culturally significant artifact. No official archaeological investigation or preservation effort has been undertaken. The site remains a popular tourist destination for experienced scuba divers, particularly during the winter months when hammerhead sharks are present, but it has no legal protection as a historical site, and yet the debate refuses to settle. Supporters of the artificial theory, including authors like Graham Hancock, point out that while many individual features of the monument can be found in natural sandstone formations around the world, the concentration of so many of them in such a small area is, at the very least, remarkable. They also note the relative absence of loose rubble on the flat surfaces of the formation, rubble that would be expected if the steps were formed entirely by natural fracturing and erosion. The steps are clean, almost swept, as though maintained or, at minimum, as though the forces that shaped them were unusually thorough. The truth, as with so many ocean mysteries, likely sits somewhere in the middle. The Yonaguni monument may be a natural formation that was noticed, and perhaps modified by ancient people, its flat surfaces and regular shapes serving as a convenient foundation for ritual or practical use. Or it may be entirely natural, a product of geology so dramatic that it mimics architecture, or less likely but not impossible, it may be something built by hands we know nothing about, in an era so distant that the builders left no other trace. Whatever it is, it sits in the clear blue water of the coast of Japan 25 meters down, waiting for someone to settle the argument, and no one has yet. From sounds in the deep Pacific that took 2 decades to explain, to structures on the seafloor that may never be explained, the ocean continues to offer evidence it refuses to interpret. And the next mystery sits even deeper, in the cold, dark waters of the Baltic Sea. In June of 2011, a Swedish ocean exploration team called Ocean X was conducting a routine treasure hunting expedition along the floor of the northern Baltic Sea, dragging side-scan sonar equipment through the cold, murky water between Sweden and Finland. The team was led by Peter Lindberg and Dennis Asberg, both experienced divers and salvage operators who had spent years searching for shipwrecks and other valuable finds on the Baltic seabed. Sonar sweeps of the ocean floor are monotonous work. Most of what they show is flat, featureless sediment, interrupted occasionally by natural rock formations or the decaying remains of sunken vessels. But on this particular sweep, something appeared on the sonar screen that was neither flat, nor featureless, nor easily explained. The image showed a large, roughly oval-shaped object resting on the seabed at a depth of about 90 meters. It was approximately 60 meters across, or about 200 feet, and it appeared to have a smooth, almost metallic-looking surface that contrasted sharply with the surrounding mud and silt. Even more unusually, the sonar data seemed to show a long track or drag mark running across the seafloor for roughly 300 meters, leading directly to the object, as though it had slid or rolled into its current position from some distance away. The team published the sonar images, and the reaction was immediate and explosive. To a casual observer, the object bore a passing resemblance to the Millennium Falcon from Star Wars, an oval shape with irregular edges and what appeared to be structural features on its surface. The internet seized on the images. Theories ranged from a natural geological formation to a sunken World War II anti-submarine device to something far more exotic. Some commentators suggested, with varying degrees of seriousness, that the Baltic Sea anomaly was a crashed UFO. In subsequent dives, OceanX reported additional strange details. They said that electronic equipment, including their satellite phone and some of their diving instruments, malfunctioned when they approached the object, though these claims have never been independently verified. They described the surface of the object as having an unusual texture, somewhere between stone and metal, with features that looked like corridors, walls, and even a staircase. Some of these descriptions came from video footage taken in the notoriously poor visibility of the Baltic Sea, where even experienced divers can mistake natural rock formations for artificial structures. Geologists who reviewed the sonar data and the available footage offered a more prosaic explanation. Several proposed that the object was a glacial deposit, a large boulder or cluster of boulders dropped onto the seafloor by retreating ice sheets at the end of the last ice age, roughly 10 to 12,000 years ago. The Baltic Sea was covered by a massive ice sheet during the Pleistocene, and when the ice melted it deposited enormous quantities of rock and sediment in random patterns across the seabed. The drag mark behind the object could be consistent with a large rock being pushed along the seafloor by moving ice, before being deposited in its current location. Others suggested the object might be a natural rock formation shaped by underwater currents and sedimentation, or possibly the remains of a concrete structure from the Second World War. The Baltic Sea was one of the most heavily contested naval theatres of both world wars, and the seabed is littered with military debris, including mines, depth charges, and the wrecks of submarines and surface vessels. No definitive scientific study of the Baltic Sea anomaly has been published. OceanX conducted several diving expeditions to the site, but never recovered a sample of the object for laboratory analysis. Independent researchers have not been granted access to the site under controlled conditions. The poor visibility and strong currents of the northern Baltic make detailed underwater examination extremely difficult. As a result, the anomaly remains in a kind of scientific limbo, too unusual to dismiss entirely, but too poorly documented to confirm as anything other than a natural formation. What the Baltic Sea anomaly illustrates, perhaps more than any specific conclusion, is how quickly the human mind reaches for extraordinary explanations when confronted with something unfamiliar in the ocean. The seabed is vast, dark, and almost entirely unseen by human eyes. When sonar or cameras reveal something unexpected, the urge to interpret it as meaningful, as built, as alien, is nearly irresistible. But the ocean floor is a place where natural processes routinely produce formations that look designed. Ice, water, pressure, and millions of years of sedimentation can create shapes that fool even trained eyes. The Baltic Sea anomaly may be a glacial erratic. It may be a wartime relic. It may be something else entirely. What it almost certainly is not is a spacecraft. But its mystery endures because no one has been able to prove conclusively what it actually is. And in a body of water as opaque and secretive as the Baltic, that ambiguity is likely to persist for a very long time. If the Baltic Sea guards its secrets behind murky water and poor visibility, the next location on our journey keeps its mysteries through sheer crushing depth, a place so deep and so hostile that reaching it requires technology normally associated with space exploration, a place where the pressure would crush a human body in an instant, where the temperature hovers just above freezing, and where sunlight has never once penetrated. The Mariana Trench. It sits in the western Pacific Ocean, east of the Mariana Islands and roughly 200 miles southwest of the US territory of Guam. The trench itself is a crescent-shaped scar in the Earth's crust, formed by the collision of two tectonic plates, where the Pacific Plate dies beneath the smaller Mariana Plate in a process called subduction. This geological collision has been occurring for millions of years, and it has produced the deepest known depression on the surface of the planet. The trench is enormous. It stretches approximately 1,580 miles in length and averages about 43 miles in width. But it is the depth that defines it. The deepest point, a narrow slot at the southern end called the Challenger Deep, plunges to 35,876 feet below sea level, or roughly 10,935 meters. To put that in perspective, if you placed Mount Everest, the tallest mountain on Earth, into the Challenger Deep with its base on the bottom, the peak would still be submerged under more than a mile of water. The trench was first measured in 1875 by the crew of HMS Challenger, a British Royal Navy corvette converted into a research vessel for one of the first true oceanographic expeditions. Using weighted sounding lines, the crew recorded a depth of over 26,000 feet, a number so extreme that many scientists of the era doubted it. It would take another 80 years before anyone attempted to visit the bottom in person. On January 23, 1960, Swiss oceanographer Jacques Piccard and US Navy Lieutenant Don Walsh descended into the Challenger Deep aboard the Trieste, a specially designed deep-sea submersible called a bathyscaphe. The descent took nearly 5 hours. At the bottom, the water pressure was approximately 16,000 pounds per square inch, more than 1,000 times the standard atmospheric pressure at sea level. The two men spent only about 20 minutes on the bottom before beginning their slow ascent. Through the small observation window of the Trieste, Piccard reported seeing a flat fish, possibly a sole or a flounder, resting on the sediment. It was the first evidence that life existed at the very deepest point on Earth, a finding that astonished biologists who had assumed the pressures were too extreme for anything to survive. More than 50 years passed before anyone returned. In March 2012, filmmaker James Cameron piloted the Deep-Sea Challenger, a specially built vertical torpedo-shaped submersible to a depth of 35,756 feet, making him the third person ever to reach the Challenger Deep and the first to do so alone. Cameron spent several hours on the bottom, collecting samples and filming footage of the alien landscape. He described the experience as desolate and isolating, a world of absolute darkness broken only by the lights of his craft, with fine pale sediment covering a flat, featureless plain. What Cameron and subsequent robotic expeditions have revealed is that even in the most extreme conditions on Earth, life persists. The Challenger. Deep is home to a range of organisms adapted to pressures and temperatures that would be instantly lethal to surface creatures. Xenophiophores, single-celled organisms the size of a human fist, have been found scattered across the trench floor, feeding on the thin rain of organic particles that drifts down from the surface thousands of meters above. Amphipods, small crustaceans resembling shrimp, scavenge in the sediment. In 2019, an expedition led by explorer Victor Vescovo recorded a new species of snailfish swimming at a depth of more than 26,000 feet, making it one of the deepest living fish ever observed. But the Mariana Trench holds mysteries that go beyond biology. Near the bottom of the trench, researchers have discovered phenomena that have no equivalent anywhere else on the planet. Deep-sea hydrothermal vents, where superheated water laced with minerals erupts from cracks in the Earth's crust, create oases of chemical energy that support entire ecosystems in total darkness. The water emerging from these vents can reach temperatures of 371 degrees Celsius, more than 700 degrees Fahrenheit. Yet it does not boil because the crushing pressure at that depth raises the boiling point far above its surface equivalent. Perhaps the strangest feature of the trench is the presence of brine pools, bodies of water so saturated with dissolved salt and minerals that they form distinct underwater lakes on the ocean floor, complete with their own shorelines and surfaces. The brine in these pools is roughly 10 times saltier than the surrounding seawater, and the density difference between the two is so extreme that they do not mix. A submarine passing over a brine pool would see a clear shimmering surface below it, an underwater lake within the ocean itself. The edges of these pools are often lined with the preserved remains of fish, crabs and other creatures that wandered too close and were killed by the toxic concentration of salt and methane. Scientists have nicknamed one of the most well-known brine pools the Jacuzzi of Despair. The origin of the brine is still debated. Some researchers believe it seeps from ancient salt deposits trapped beneath the seafloor, remnants of evaporated seas from millions of years ago. Others think tectonic activity forces mineral-laden water up through cracks in the crust. The full chemistry of these pools and the nature of whatever might live in their most concentrated depths remains unknown. No human expedition has sampled the deepest layers of a deep-sea brine pool. The technology to do so exists in theory, but has not been deployed. The Mariana Trench represents, in many ways, the final frontier of Earth-based exploration. Less than a dozen people have ever visited the Challenger Deep. More have walked on the surface of the Moon. The conditions at the bottom of the trench are so extreme that equipment designed for deep-sea work must be built to standards comparable to spacecraft. Even remotely operated vehicles struggle. In 2014, NOAA's Deep Discoverer ROV, exploring a section of the Mariana Trench at a depth of about 12,000 feet, encountered a gelatinous, translucent organism that researchers were unable to identify. Footage of the encounter went viral, the creature drifting slowly through the pitch-black water, glowing faintly in the ROV's lights, looking less like something from this planet than from another world entirely. What else lives in the Mariana Trench remains largely unknown. What geological processes are occurring at its deepest points remain poorly understood. The trench is a place where the rules of biology, chemistry and physics operate at their most extreme, and every expedition that descends into it returns with more questions than it set out with. The pressure down there is roughly 8 tons per square inch. The temperature is a degree or two above freezing. The darkness is total and permanent, and in that environment life has found a way. What forms that life takes in the sections of the trench that no camera has yet reached and no submersible has yet visited is anyone's guess. And while scientists probe the deepest points on the planet with billion-dollar technology, the ocean has a way of surfacing its mysteries in far more personal ways. Sometimes it is not the depth that disturbs, but the silence. The eerie, inexplicable emptiness of a vessel found adrift with no one aboard. The ghost ships of the deep have a long and unsettling history, and the Mary Celeste was only the beginning. In the spring of 1968, the Cold War was at one of its most tense periods. The Tet Offensive had shaken American confidence in Vietnam. The Soviet Union was flexing its naval power across every ocean. And beneath the surface of the Atlantic, American and Soviet submarines played a silent, deadly game of cat and mouse, tracking each other through the deep with sonar and intuition, each side testing the other's limits, while trying never to cross the line into open conflict. It was into this environment that the USS Scorpion, a Skipjack-class nuclear-powered attack submarine, set out from the Mediterranean on her return voyage to Norfolk, Virginia. The Scorpion was a fast, capable boat. She had been commissioned in 1960 and had spent the better part of a decade conducting surveillance operations, training exercises, and Cold War patrols in the Atlantic and Mediterranean. Her crew of 99 men was experienced. Her commanding officer, Commander Francis Slattery, was well regarded. The submarine had completed a deployment in the Mediterranean and was heading home. On May 21, 1968, Slattery sent a routine message reporting his position and estimated time of arrival in Norfolk. He expected to reach port on May 27th. He never arrived. When the Scorpion failed to appear at the appointed time, the Navy launched one of the largest submarine searches in history. Ships, aircraft, and other submarines fanned out across the Scorpion's projected route, listening for any sign of the boat or her crew. For 5 months they found nothing. Then in October 1968, a deep-sea search operation using towed camera sleds located the shattered wreck of the Scorpion on the ocean floor, roughly 400 miles southwest of the Azores, at a depth of more than 10,000 feet. The hull had imploded from the crushing water pressure, and the wreckage was spread across a wide area of the seabed. The Navy convened a court of inquiry. The proceedings were classified. The conclusions, when they were eventually made public in incomplete form, stated that the cause of the loss could not be determined with certainty. Several theories were considered. A torpedo malfunction, in which one of the Scorpion's own torpedoes armed itself and detonated inside the boat, was one possibility. Mechanical failure, particularly a failure of the submarine's trash disposal unit that could have led to flooding, was another. A third theory, never officially endorsed but widely whispered in naval circles, held that the Scorpion had been attacked by a Soviet submarine. The Soviet attack theory has never been substantiated. No Soviet vessel has been publicly linked to the loss, and the Russian government has denied any involvement. But the timing was suspicious. Just 2 months before the Scorpion vanished, in January 1968, a Soviet Golf-class ballistic missile submarine had sunk in the Pacific Ocean under mysterious circumstances. The United States had secretly located the wreck and was planning a covert recovery operation that would eventually become known as Project Azorian. Some have speculated that the Soviets knew about the American discovery, and that the loss of the Scorpion was retribution, a Cold War quid pro quo that both sides agreed to keep silent about. None of this has ever been proven. The Navy's official position remains that the cause of the Scorpion's loss is undetermined. The wreck sits on the floor of the Atlantic, too deep for easy recovery, a tomb for 99 men whose families were given a flag and an explanation that amounted to a shrug. Nothing definitive has ever been announced, and the classified portions of the Court of Inquiry remain sealed. The loss of the Scorpion was not an isolated event. In that same year, 1968, 3 other submarines were lost at sea. The Israeli submarine Wudai NS Dakar vanished in the Mediterranean in January. The French submarine Minerve was lost the same month, and the Soviet Golf-class submarine mentioned earlier sank in the Pacific in March. 4 submarines from 4 different nations, gone in the span of a few months. Whether this was coincidence, consequence, or something else entirely has been debated for more than half a century. The Scorpion's resting place in the deep Atlantic is one of the ocean's quieter monuments. There are no plaques, no markers, just a scattered field of metal on the seafloor, slowly being buried by silt, holding its secrets the way the ocean always does, in silence. Far from the cold, contested waters where the Scorpion met her end, there is a place in the Atlantic that is strange, for an entirely different reason. Not because of what it hides, but because of what it is, a sea without shores. The Sargasso Sea occupies a vast elliptical region of the North Atlantic, roughly 700 miles wide and 2,000 miles long, centered in the area between the Azores and the Caribbean. What makes it unique among all the seas on Earth is that it has no land boundaries. It is defined entirely by the ocean currents that surround it. On the west and north, the powerful Gulf Stream sweeps along its edge. To the east, the Canary Current flows southward. To the south, the North Atlantic Equatorial Current completes the circuit. These four currents form a vast, slow-rotating gyre that traps the water within the Sargasso Sea in a kind of liquid enclosure, isolating it from the rest of the Atlantic. The result is a body of water that is calmer, clearer, warmer, and saltier than the ocean that surrounds it. The surface is covered in thick mats of free-floating sargassum seaweed, a golden-brown algae that gives the sea its name. Christopher Columbus and his crew encountered the Sargasso Sea during their first voyage to the Americas in 1492, and the sight of vast stretches of floating weed in the middle of the open ocean alarmed them. Some sailors believed the weed would entangle their ships and trap them forever. Others took it as a sign that land was nearby. Both assumptions were wrong. For centuries, the Sargasso Sea occupied a peculiar place in maritime folklore. Sailors told stories of ships becoming permanently stuck in the weed, their crews starving to death as the calm winds of the gyre left them becalmed. The reality is less dramatic, but no less fascinating. The Sargasso Sea is indeed calmer than the surrounding Atlantic, and during the age of sail ships could be becalmed, there for days or weeks, waiting for wind to fill their sails. But the weed, while extensive, is not thick enough to physically trap a vessel. The stories were exaggerations born from the fear and frustration of being stuck in a windless stretch of water with no land in sight. What the Sargasso Sea actually harbours is one of the most extraordinary biological mysteries in the ocean. The European eel, a fish found in rivers and streams across Europe, migrates thousands of miles across the Atlantic to the Sargasso Sea to spawn. The journey takes months, and the eels stop eating along the way, surviving on stored fat. When they reach the warm, weed-choked waters of the Sargasso, they reproduce, and then they die. Their tiny larvae, transparent and leaf-shaped, drift back across the Atlantic on the ocean currents, a journey that can take up to 3 years, before arriving in European coastal waters and beginning the transformation into the juvenile eels that eventually swim upstream into the rivers where their parents were born. This life cycle was not fully understood until the early 20th century, when Danish biologist Johannes Schmidt spent nearly 20 years tracking the diminishing size of eel larvae across the Atlantic, eventually determining that the Sargasso Sea was the only place where the smallest, youngest larvae could be found. Even today, no one has ever observed European eels spawning in the wild. The exact locations within the Sargasso Sea where they reproduce, the depth at which spawning occurs, and the precise mechanisms that guide the larvae back to Europe remain unknown. The Sargasso Sea is also an ecological treasure in its own right. The floating sargassum provides shelter and food for more than 120 species of fish, as well as sea turtles, shrimp, crabs, and a wide variety of invertebrates. Humpback whales pass through on their annual migrations. Endangered species use the weed mats as nurseries. The water beneath the surface is among the clearest in the Atlantic, with visibility extending to depths that are rare in the open ocean. But the Sargasso Sea is also under threat. In recent years, massive blooms of sargassum have been washing ashore across the Caribbean and the Gulf of Mexico in unprecedented quantities, smothering beaches, killing marine life, and producing toxic hydrogen sulfide gas as the weed decomposes. Scientists are still trying to determine what is driving these blooms, with leading theories pointing to increased nutrient runoff from rivers, changes in ocean circulation patterns, and rising sea surface temperatures. The Sargasso Sea, a place that has puzzled sailors for 5 centuries, is now puzzling scientists for entirely new reasons. And if the Sargasso Sea is strange for what it traps, there is another ocean phenomenon that is strange for what it produces, a glow so vast and so bright that it can be seen from space. The Milky Sea phenomenon is one of the oldest documented oddities of the ocean, For more than 400 years, sailors have reported encountering vast stretches of water that glow with a steady, pale, milky white luminescence. The glow is not the flickering sparkle of bioluminescent plankton that many people have seen in coastal waters at night, triggered by the movement of waves or a passing boat. The Milky Sea is different. It is a continuous, uniform glow that extends in every direction to the horizon, turning the surface of the ocean into a flat, featureless sheet of white light. Sailors who have witnessed it describe the sensation as deeply unsettling, like sailing across an endless field of glowing milk. Some have reported that the light is bright enough to read by. For centuries, the phenomenon was dismissed by many scientists as exaggeration or misperception, but in 2005, researchers analysing satellite imagery confirmed that a Milky Sea event had occurred in the Indian Ocean off the coast of Somalia in January of that year. The satellite data showed a glowing patch of water covering more than 15,000 square kilometres, an area roughly the size of Connecticut. The glow was visible in nighttime satellite images taken from orbit, making it one of the few biological phenomena on Earth that can be detected from space. The cause of the Milky Sea is now understood to be bioluminescent bacteria, specifically a species called Vibrio harveyi. These bacteria produce light through a chemical reaction involving an enzyme called luciferase, similar to the process used by fireflies. But there is a crucial difference. Unlike plankton, which glow in brief flashes when mechanically disturbed, Vibrio harveyi produce a continuous, steady glow. The bacteria achieve this through a process called quorum sensing, in which individual cells detect the concentration of signaling molecules produced by neighbouring cells. When the population reaches a critical density, the bacteria coordinate their behaviour and switch on their light-producing genes simultaneously. The result is a uniform glow across an enormous area of water. What triggers these mass-blooming events is still not fully understood. The bacteria are normally present in seawater at low concentrations, producing no visible light. Something causes their numbers to explode into the billions, reaching concentrations so extreme that the collective glow becomes visible to the naked eye and even to orbiting satellites. Some researchers believe the blooms may be associated with the presence of large quantities of dead organic matter, perhaps from algal die-offs, that provide the nutrients the bacteria need to multiply rapidly. Others suspect that specific combinations of water temperature, salinity, and nutrient availability create conditions that favour explosive growth, but the exact triggering mechanism remains elusive. The Milky Sea has been reported most frequently in the northwestern Indian Ocean, in the waters between the Horn of Africa and the Indian subcontinent, though isolated reports have come from other tropical and subtropical regions. Sightings seem to be more common during the monsoon season, when upwelling brings nutrient-rich water from the deep ocean to the surface. But not every monsoon season produces a Milky Sea event, and not every nutrient upwelling leads to a bacterial bloom. The phenomenon appears to be rare, unpredictable, and governed by conditions that science has not yet fully mapped. For those who have seen it, the experience is unforgettable. A ship surrounded on all sides by glowing white water, the horizon erased, the boundary between sea and sky dissolved into a single field of light. It is one of those moments when the ocean reminds you that it operates according to rules you have not yet learned, and while the Milky Sea glows on the surface, the ocean has a long history of producing another kind of spectacle entirely. Not light, but absence. Ships found drifting, intact. Their crews vanished without explanation. The Mary Celeste was the most famous, but she was far from the only one. The ocean's ledger of ghost ships is longer and more disturbing than most people realise. The Mary Celeste is the ghost ship the world remembers. But the ocean has produced others, each one carrying its own impossible silence, its own unanswered departure. And 3 of them deserve to be told here, because each represents a different flavour of the same fundamental mystery. People aboard a ship, the ship found later, the people gone. The first is the Carroll A. Deering, a 5-masted commercial schooner built in Bath, Maine in 1919. She was a large, handsome vessel, 255 feet long, designed for carrying cargo along the Atlantic coast. In late January 1921, the Deering was spotted by a lightship keeper at Cape Lookout, North Carolina, sailing northward under full canvas. The keeper noted that the crew appeared to be milling about on the forward deck, which was unusual. The quarterdeck, where the ship's officers would normally be stationed, was deserted. A crew member hailed the lightship through a megaphone and reported that the ship had lost her anchors. 2 days later, on January 31st, 1921, the Carroll A. Deering was found grounded on Diamond Shoals, a treacherous sandbar off the coast of Cape Hatteras. When a boarding party from the Coast Guard reached the vessel, they found her in a condition eerily similar to the Mary Celeste. The ship was abandoned. Not a single one of the 11 crew members was aboard. The lifeboats were gone. The crew's personal effects had been left behind. In the galley, food had been laid out as though a meal was being prepared. The ship's navigation equipment was missing, and the log charts and personal papers of the captain had been removed. The steering wheel was not lashed, meaning no one had secured it before leaving. And most disturbingly, the ship's 2 cats were still aboard, alive and prowling the empty decks. The investigation that followed was one of the most extensive in American maritime history. 5 government agencies were involved, including the FBI, the State Department, and the Commerce Department. Theories range from piracy to rum running to mutiny. The Deering had been sailing through waters frequented by bootleggers during Prohibition, and some investigators believed the crew had been taken by pirates or rivals in the illegal liquor trade. Others noted that the ship's captain, Willis Warmall, had complained before the voyage about difficulties with his first mate, Charles McClellan, raising the possibility of mutiny. One investigator found what appeared to be a message in a bottle washed ashore near the wreck site, claiming the crew had been taken by an oil-burning boat, but the message was later determined to be a forgery. In the end, the investigation produced no definitive answers. The Carroll A. Deering was dynamited and destroyed where she lay grounded on Diamond Shoals, as she had become a hazard to navigation. The 11 men who had sailed aboard her were never found, and no credible explanation for their disappearance has ever been established. The case remains officially unsolved. The second ghost ship sailed even farther from any resolution. The SS Waratah was a 465-foot passenger and cargo liner operated by the Blue Anchor Line, making regular voyages between England, South Africa, and Australia. She was relatively new, having been launched in 1908, and she was well appointed for her time, carrying both passengers and refrigerated cargo. On July 26, 1909, the Waratah departed Durban, South Africa, bound for Cape Town with 211 people aboard, passengers and crew. She was never seen again. The last confirmed sighting of the Waratah came from another ship, the Clan McIntyre, which exchanged signals with her on the morning of July the 27th, about 180 miles south of Durban. After that, the Waratah sailed into what witnesses described as deteriorating weather and simply vanished. No distress signal was sent, no wreckage was found, no bodies washed ashore. Despite one of the most extensive sea searches in South African history, involving multiple naval and civilian vessels combing the coastline and open water for weeks, not a single piece of the Waratah or evidence of her fate was ever recovered. Theories centered on the possibility that the ship had been struck by a rogue wave or had capsized in heavy seas. Some passengers who had sailed on the Waratah's earlier voyages reported that the ship had a tendency to roll heavily and was slow to right herself, a characteristic known as being tender. One passenger, an engineer named Claude Sawyer, had been so alarmed by the ship's behaviour on a previous leg of the same voyage that he disembarked in Durban rather than continue to Cape Town. Sawyer later testified at the Board of Trade inquiry that he had experienced a vivid premonition of disaster and had dreamed repeatedly of the ship rolling over and sinking. The inquiry, which took place in London in 1910 and 1911, heard extensive testimony about the Waratah's stability, but reached no definitive conclusion about what had caused the loss. The ship was presumed to have foundered in heavy weather, but without wreckage it was impossible to determine the precise mechanism. In the decades since, several expeditions have searched for the wreck using sonar and submersible technology. None have found it. The SS Waratah, a 465-foot steel ship carrying more than 200 people, has simply never been located. The third ghost ship is smaller in scale but no less perplexing. In October 1955, a 69-ton motor vessel called the MV Joyita departed the port of Apia in what was then Western Samoa, bound for the Tokelau Islands, a journey of roughly 270 miles across the South Pacific. Aboard were 25 people, including passengers and crew, along with a cargo of timber, food supplies and medical equipment. The Joyita never arrived. A search by the Royal New Zealand Air Force found nothing. 5 weeks later, on November 10th, the ship was discovered drifting 600 miles west of her intended route, partially waterlogged and listing heavily to one side. Her port engine was covered with mattresses, suggesting the crew had been trying to stop a leak. The radio was tuned to the international distress frequency, but no distress call had been received by any station. The clocks on board had stopped at different times, indicating a gradual flooding rather than a sudden catastrophe, and critically, the ship's hull was lined with cork, making her virtually unsinkable. Even in her waterlogged state, the Joyita was still afloat when she was found, but all 25 people were gone. The lifeboats were missing. The cargo was gone. No bodies were ever recovered. The most widely accepted theory is that a pipe failure in one of the engine cooling systems caused a slow, steady leak that flooded the engine room. As the ship listed and settled lower in the water, the captain may have ordered the passengers and crew into the lifeboats, either intending to be rescued or to make for a nearby island. But the Joyita was still floating, and abandoning a floating ship for a small lifeboat in the open Pacific is almost always a fatal decision. Wherever the 25 people went after they left the Joyita, they were never seen again. 3 ships, 3 different oceans, 3 separate decades, and in each case, the same impossible silence. A vessel found, the people gone, the ocean offering no explanation and no remains. These stories carry a particular kind of dread because they invert our expectations. A shipwreck is tragic but comprehensible. We understand storms, collisions, fires. We understand sinking. What we do not understand is leaving. What force, what fear, what miscalculation could compel an entire crew to abandon a ship that was still afloat and still capable of carrying them to safety? That is the question the ocean asks with every ghost ship it produces, and it has never once provided a satisfying answer. The water takes what it wants. And sometimes, what it takes is not the ship, but the people. If ghost ships represent the ocean's cruelest trick, there are creatures living in its depths that represent something gentler, but equally mysterious. Animals so old that the concept of a human lifetime becomes almost meaningless next to them, and none is more extraordinary in its longevity than the Greenland shark. The Greenland shark is a massive, slow-moving predator found in the deep, frigid waters of the North Atlantic and Arctic Oceans. Adults can grow to more than 20 feet in length and weigh over a ton, making them one of the largest shark species on Earth. They are rarely seen by humans because they spend most of their lives at depth between 600 and 2,400 feet, far below the reach of recreational divers in water so cold that most other large predators cannot survive. They swim slowly, averaging less than 1 mile per hour, cruising through the darkness with a patience that, as it turns out, is built into the very fabric of their biology. In 2016, a landmark study published in the journal Science revealed something about the Greenland shark that stunned the scientific world. Using a technique called radiocarbon dating on crystalline proteins found in the lenses of the shark's eyes, a team of researchers led by marine biologist Julius Nielsen determined that the Greenland shark has the longest known lifespan of any vertebrate animal on the planet. The oldest specimen in the study was estimated to be approximately 392 years old, with a margin of error that could push her true age to nearly 500 years. That would mean she was born in the early 17th century, around the time Shakespeare was writing his plays and the Pilgrims were sailing for the New World. Even more remarkably, the study found that Greenland sharks do not reach sexual maturity until they are approximately 150 years old, a century and a half of life before they are biologically ready to reproduce. By human standards, that is the equivalent of entering adulthood somewhere around the year 1870 for a shark born today. It is a reproductive strategy that is almost incomprehensibly slow, and it raises serious questions about the species' ability to recover from population declines. The mechanism behind this extraordinary longevity is not fully understood. Researchers believe it is related to the shark's extremely slow metabolism, which is itself a consequence of living in near-freezing water. Cold-blooded animals in cold environments burn energy at a fraction of the rate of their warmer counterparts, and this reduced metabolic rate appears to slow the aging process as well. The Greenland shark's heart beats only a few times per minute. Its digestion can take weeks. Everything about it operates on a time scale that is, to a human observer, almost geological. The shark's eyes offer another clue to their peculiar biology. Most Greenland sharks are partially or completely blind, their corneas scarred by a parasitic copepod called Omatocoeta elongata that attaches itself to the shark's eye and feeds on the corneal tissue. The parasite is so common that nearly all adult Greenland sharks carry at least one. Despite this, the sharks do not appear to be significantly handicapped by the loss of vision, suggesting that they rely primarily on smell and lateral line detection to find food in the perpetual darkness of their habitat. The diet of the Greenland shark is as bizarre as the animal itself. Stomach contents have revealed fish, seals, reindeer, moose, and even polar bears, though it is believed that much of this is scavenged from carcasses that sink to the bottom, rather than actively hunted. The sharks have been found with entire caribou legs in their stomachs, presumably from animals that fell through ice or drowned while crossing rivers. In one famous case, a Greenland shark was found with an entire reindeer in its gut, antlers and all. Despite their size and longevity, Greenland sharks are increasingly threatened by human activity. They are caught as bycatch in deep water fishing operations and are vulnerable to pollution and climate change. Their extraordinarily slow reproductive rate means that populations depleted by overfishing could take centuries to recover, if they recover at all. A species that has survived every extinction event of the last 400 million years, that was swimming in these waters when the Vikings sailed to Greenland and when the Roman Empire fell, is now facing threats that operate on a timescale it was never evolved to handle. The Greenland shark is a reminder that the ocean operates on its own clock. While human civilizations rise and fall in the span of a few centuries, these animals drift through the deep on a timeline that makes our history look like a footnote. They were here before us. They will very likely be here after, and what they have witnessed in their centuries of slow, dark swimming, we will never know. If the Greenland shark represents life stretched to its extreme, the next wonder sits on the ocean floor itself, in places so hostile that life should not exist at all. And yet it does. Deep beneath the surface of the ocean, in places where sunlight has never reached and the pressure would crush a human body in an instant, there are lakes. Not metaphorical lakes, not poetic descriptions. Actual bodies of water sitting on the ocean floor with their own shorelines, their own surfaces, and their own deadly chemistry. They are called brine pools, and they are among the strangest natural phenomena on Earth. A brine pool forms when salt, usually from ancient geological deposits buried beneath the seabed, dissolves into seawater that has seeped down through cracks in the ocean floor. The resulting liquid is so saturated with dissolved minerals, primarily sodium chloride, magnesium and other salts, that it becomes dramatically denser than the seawater surrounding it. The density difference is so extreme that the brine and the normal ocean water do not mix. They sit in distinct layers, the heavy brine pooling at the bottom, the lighter seawater resting above it, with a thin shimmering boundary between them that looks, from the perspective of a submersible or a camera, exactly like the surface of a lake. The first brine pools were discovered in the Gulf of Mexico in the 1980s during deep-sea surveys conducted by research submarines. Scientists were stunned. The pools had clear, visible shorelines where the brine lapped against the surrounding seafloor. In some cases, the brine was so dense and so stable that it formed ripples on its surface when disturbed, just like a lake on land. Submersibles could lower instruments into the brine and measure the exact point where the chemistry changed, a transition so sharp that it occurred over a distance of just a few centimeters. The concentration of salt in these pools is staggering. Normal seawater has a salinity of about 35 parts per thousand. The brine in deep-sea pools can reach 300 parts per thousand, or more, nearly 10 times saltier than the surrounding ocean. The pools also contain elevated levels of methane and hydrogen sulfide, both of which are toxic to most marine life. The result is an environment so hostile that almost nothing can survive in it. Fish, crabs, and other organisms that wander too close to a brine pool are quickly overcome by the toxic chemistry and die. Their preserved remains often line the edges of the pools in eerie accumulations, giving the shorelines a graveyard quality that has earned at least one well-known brine pool in the Gulf of Mexico the nickname Jacuzzi of Despair. And yet, life exists even here. At the extreme edges of some brine pools, where the toxic brine begins to mix with normal seawater in a thin transitional zone, researchers have found dense communities of specialized organisms. Mussels, tube worms and certain species of bacteria thrive in these margins, drawing energy not from sunlight, which is completely absent at these depths, but from the chemical reactions between the brine's dissolved gases and the surrounding water. This process, called chemosynthesis, is the same mechanism that supports life around hydrothermal vents and is considered one of the leading models for how life might exist on other worlds, particularly on the ocean moons of Jupiter and Saturn. The interiors of brine pools, however, remain largely unexplored. The brine itself is so dense and so corrosive that it can damage instruments and interfere with the propulsion systems of deep-sea vehicles. No human expedition has sampled the deepest layers of a major brine pool. What might exist in those concentrated, oxygen-free environments, whether extremophile organisms have found a way to survive in conditions that would kill everything else on the planet, is simply not known. The technology to find out exists in principle, but deploying it to the necessary depths, in the necessary conditions, has not yet been achieved. Brine pools remind us that the ocean floor is not a uniform, featureless wasteland. It is a landscape of extraordinary variation, with its own mountains, valleys, volcanoes, and now lakes. Lakes that kill, lakes that glow with chemical energy, lakes that sit in total darkness at the bottom of the world, waiting for someone to look closer. If the ocean floor can hide entire lakes that we did not know existed until a few decades ago, it should come as no surprise that the surface of the ocean has its own vanishing acts, and one of the strangest involves an island that appeared on maps for nearly 500 years and then, when someone finally went to look for it, was simply not there. Bermeja was, supposedly, a small island in the Gulf of Mexico, situated roughly 100 miles northwest of the Yucatan Peninsula. It first appeared in a list of islands, published in Madrid in 1539, compiled as part of the Spanish Empire's efforts to catalogue its territories in the New World. From that point on, Bermeja appeared consistently on maps of the Gulf of Mexico for the next 4 centuries. Spanish, French, British, and later Mexican cartographers all included it. It was listed in official navigational charts well into the 20th century, but no modern survey has ever found it. In the 1990s and 2000s, the question of Bermeja's existence became a matter of significant political and economic importance. Mexico and the United States were negotiating the boundary of their respective exclusive economic zones in the Gulf of Mexico, a boundary that determines which country has the right to exploit undersea oil and natural gas reserves. If Bermeja existed, Mexico's economic zone would extend significantly farther into the Gulf, encompassing a region believed to contain substantial oil deposits. If it did not, the boundary would shift in favor of the United States. The Mexican government dispatched several expeditions to locate the island. The National Autonomous University of Mexico sent research vessels to the coordinates where Bermeja should have been. They found nothing but open water. The seafloor beneath the site showed no sign of a submerged landmass, no volcanic remnant, no coral atoll, no geological foundation that might have once supported an island above the waves. Bermeja, it appeared, had either never existed, or it had vanished so completely that no trace of it remained. Several theories have been proposed. The most straightforward is that the island was never real, that it was a cartographic error, a phantom island recorded by early map makers who relied on inaccurate or second-hand information, and whose mistakes were dutifully copied by subsequent generations of cartographers without anyone ever verifying the original claim. Phantom islands are more common in historical cartography than most people realize. For centuries, the Pacific Ocean was peppered with islands on maps that did not correspond to anything above the waterline, products of miscalculated positions, misidentified cloud formations, and the optimism of explorers who wanted to find land where there was none. A second theory holds that Bermeja did once exist, but has since disappeared beneath the waves due to rising sea levels, subsidence, or erosion. Small, low-lying islands in the Gulf of Mexico are particularly vulnerable to these forces, but no geological evidence of a former island has been found at the site, and the water depth in the area is sufficient to make a natural disappearance unlikely within the historical time frame. And then there is the third theory, the one that has attracted the most attention and the least evidence. It suggests that the island was deliberately destroyed, perhaps by the US government, to eliminate Mexico's claim to the oil-rich waters surrounding it. This theory has been promoted by some Mexican politicians and journalists, but has never been supported by any credible evidence. The logistics of secretly demolishing an island, even a small one, and leaving no trace whatsoever are formidable, and no whistleblower document or physical evidence has ever emerged to suggest it occurred. Bermeja remains officially listed as unlocated. It is one of those curiosities of the ocean that sits at the intersection of history, politics, and mystery. A place that existed on paper for 5 centuries and apparently nowhere else. From vanishing islands to vanishing species, the ocean's mysteries are not always ancient. Some of them are unfolding right now, in real time, and the one that has marine biologists most alarmed involves a creature that most people would recognize on sight, but few would think to worry about. Sea stars, the 5-armed invertebrates that most of us grew up calling starfish, are found in oceans around the world, from tropical shallows to deep polar waters. They are slow, patient predators, feeding primarily on mussels, barnacles, and other hard-shelled organisms by prying them open with their powerful arms and extruding their stomachs into the shell to digest the animal inside. They are also ecologically critical. In many coastal ecosystems, sea stars are keystone species, meaning they play such a central role in controlling the populations of other organisms that their removal can cause the entire ecosystem to collapse. Beginning in 2013, sea stars along the Pacific coast of North America began dying in enormous numbers. The disease, which came to be known as sea star wasting syndrome, was horrific in its presentation. Affected animals developed white lesions on their arms and bodies. The lesions spread rapidly, and within days the tissue began to dissolve. Arms fell off. The body deflated. The animal literally disintegrated, melting into the substrate until nothing recognizable remained. The die-off was unprecedented in scale. It affected more than 20 species of sea star across a range stretching from Alaska to Baja California. In some areas, populations declined by more than 90%. The sunflower sea star, one of the largest and most ecologically important species on the Pacific coast, was so devastated that it was listed as critically endangered. The scientific community mobilized rapidly. Researchers collected samples, ran tests, and examined environmental data looking for the cause. Early investigations suggested a viral pathogen, a sea star-associated densovirus, might be responsible, and a 2014 study published in the Proceedings of the National Academy of Sciences identified the virus in affected populations. But subsequent research failed to consistently replicate the finding, and many infected animals tested negative for the virus. Other hypotheses were advanced. Bacterial infection, genetic susceptibility, environmental stresses such as rising ocean temperatures, which were known to be at record levels during the outbreak years. As of 2024, no single cause has been definitively identified. The prevailing scientific view is that sea star wasting syndrome is likely the result of multiple interacting factors, a combination of pathogen, environmental stress, and possibly compromised immune function that together overwhelm the animal's ability to survive. But that is a description, not an explanation. The triggering mechanism, the specific sequence of events that turns a healthy sea star into a dissolving heap of tissue in a matter of days, remains unknown. The die-off has had cascading effects. In areas where sunflower sea stars have disappeared, populations of purple sea urchins have exploded, unchecked by their primary predator. The urchins, in turn, have devoured vast stretches of kelp forest, transforming rich, productive underwater ecosystems into barren expanses of bare rock known as urchin barrens. The loss of kelp affects fish populations, marine mammals, and the overall health of the coastal ocean. It is a vivid, real-time demonstration of what happens when a keystone species is removed from an ecosystem, and it is happening right now along one of the most studied coastlines on the planet. The sea stars are trying to recover. In some areas, juvenile sea stars have been observed in increasing numbers, suggesting that reproduction is continuing even as the disease persists. But whether the populations can rebuild fast enough to prevent permanent ecological damage is an open question, and whether the disease will return in new waves, triggered by future warming events or by mutations in whatever pathogen is responsible, is a risk that marine biologists are watching closely. The ocean is not just a place of ancient mysteries, it is a place where new ones are being born all the time, and this one, playing out in tide pools and kelp forests along a coast that millions of people visit every year, is a reminder that we do not have to go to the bottom of the Mariana Trench to find something the ocean is keeping from us. Sometimes the mystery is right at the surface, close enough to touch, dissolving before our eyes. And sometimes the mystery is not death, but behaviour. Patterns so strange that even the scientists who study them cannot explain why they exist. Which brings us to one of the most peculiar and least understood migrations in the ocean. Great white sharks are among the most recognisable and most feared predators on the planet. They patrol coastal waters on every continent except Antarctica, hunting seals, sea lions and fish in the shallow productive waters along the continental shelves. Their reputation is built on proximity. They live where we swim, surf and fish. They are the ocean's most visible apex predator. But for decades, scientists tracking the movements of great white sharks noticed something they could not explain. Every year, a significant number of the sharks tagged along the coast of California would leave the productive, food-rich waters of the coastline and swim thousands of miles into the open Pacific, heading for a remote, seemingly empty stretch of ocean roughly halfway between Baja California and Hawaii. The area had no obvious features, no seamounts, no coral reefs, no concentrations of prey. It was, by every measure that satellite data could provide, an oceanic desert. Yet the sharks went there every year, reliably and deliberately, spending weeks or months in the region before eventually returning to the coast. Researchers named the area the White Shark Cafe, partly in jest and partly because they genuinely did not know what the sharks were doing there. The cafe sits in one of the least productive stretches of the Pacific, far from the upwelling zones and nutrient currents that support the food chains coastal sharks depend on. For an animal that requires enormous caloric intake to sustain its massive body and high metabolism, the journey seemed irrational. In 2018, a major research expedition led by scientists from Stanford University's Hopkins Marine Station and the Monterey Bay Aquarium deployed advanced satellite tags on several great white sharks before their annual migration to the cafe. The tags recorded not only the sharks' positions, but also their depth, the water temperature around them, and their rate of acceleration, providing a detailed picture of what the animals were actually doing in the open ocean. The data revealed something unexpected. Male sharks were making rapid, repetitive, deep dives during the day, plunging to depths of 450 meters or more, and then racing back to the surface over and over again, up to 140 times per day. The diving pattern was consistent with foraging behavior, and researchers concluded that the males were feeding on small, deep-water organisms, possibly squid or lanternfish, that migrate upward in the water column at night and retreat to the deep during the day. The cafe, it turned out, was not as empty as it appeared from the surface. There was food down there, just not the kind visible from a satellite. But the mystery did not end there. Female great white sharks also travelled to the cafe, but they did not perform the same diving behaviour. The females stayed in shallower water and did not make the deep, rapid dives that characterised the male's activity. Researchers still do not know what the females are doing in the cafe. Mating is one hypothesis, as the congregation of males and females in the same area during the same season suggests reproductive activity, but no one has ever observed great white sharks mating in the wild, and the cafe has not yielded direct evidence of courtship or copulation. The White Shark Cafe remains one of the great behavioural mysteries of marine biology. Why do the most powerful predators in the coastal ocean leave the richest waters on the planet and swim for weeks to reach a patch of open sea that looks, from every surface indicator, like a wasteland? The deep dive data explains part of the answer, at least for the males, but the full picture, including the role of females, the potential for mating, and whether the cafe serves additional purposes that we have not yet identified, is still incomplete. And while great whites make their annual pilgrimage to an empty stretch of the Pacific for reasons we do not fully understand, a much smaller creature in the waters off Japan has been producing something even more baffling. Something so precise, so geometric, and so beautiful that when it was first discovered, researchers assumed it had to be the work of human hands, or possibly something stranger. In the waters around Amami Oshima, a subtropical island in southern Japan, divers exploring the sandy seafloor in the late 1990s began reporting the discovery of intricate geometric patterns etched into the sand at depths of roughly 10 to 30 meters. The patterns were circles, sometimes exceeding 6 feet in diameter, composed of elaborate radial ridges and valleys, arranged with a symmetry and precision that seemed impossible for any natural process. Some of the circles were decorated with fragments of shells and coral, arranged along the ridges as though they had been deliberately placed. Viewed from above, the designs resembled mandalas, crop circles, or the work of a meticulous artist. The discovery generated enormous interest and no small amount of speculation. Some observers suggested the patterns were created by ocean currents interacting with the seafloor topography. Others proposed geological explanations. A few invoked the inevitable comparison to crop circles on land and suggested the work of unknown or extraterrestrial forces. The truth, when it was eventually revealed, turned out to be more remarkable than any of those theories. The circles were the work of a single species of small pufferfish, specifically a species in the genus Torquicina that had not even been formally described by science at the time of the discovery. Males of the species, measuring only about 5 inches long, create the elaborate patterns over the course of 7 to 9 days using nothing but their fins. They swim along the seafloor in carefully controlled paths, using their pectoral fins to push sand into ridges and valleys, building the pattern outward from the centre with a consistency that would be impressive from a creature of any size. The purpose of the circles is reproduction. Once the pattern is complete, the male decorates the ridges with shell fragments and waits for a female to inspect his work. Females visit multiple circles, apparently evaluating the quality, symmetry, and ornamentation of each one before choosing a mate. The chosen circle then serves as a nest. The female lays her eggs in the fine sand at the centre, where the ridges function as a natural barrier that reduces the flow of water currents, protecting the eggs from being swept away or buried. The complexity of the behaviour is extraordinary. The pufferfish must navigate the same path dozens of times to build each ridge, maintaining consistent spacing and depth across the entire pattern. If the pattern is damaged by currents or other fish, the male repairs it. If it does not attract a mate, he abandons it and starts over in a new location. Once the eggs are laid, the male guards the nest until they hatch. The discovery was formally published in 2013 by researcher Hiroshi Kawase and colleagues, and it received widespread attention in both the scientific community and the popular press. It is one of the most elaborate examples of animal architecture ever documented, comparable in its relative complexity to the bower-building behaviour of bowerbirds in Australia. And it is a reminder that the ocean floor, even in relatively shallow, well-explored waters, can produce surprises that overturn our assumptions about what non-human creatures are capable of. The pufferfish circles are not a mystery in the traditional sense. They have been explained. But they are a mystery in a deeper sense, a reminder that the ocean is full of behaviours, processes and creations that we did not know about until someone happened to look in the right place at the right time. And if a 5-inch fish can produce architecture this sophisticated in the sand, what else might be happening on the seafloor that we have not yet stumbled upon? From the artistry of a tiny fish to the grandest question the ocean has ever posed, the next mystery is not about what happens in the water. It is about the water itself, where it came from. The Earth is about 4.5 billion years old. That number is well established by radiometric dating of the oldest known rocks and meteorites in our solar system. The planet formed from a swirling cloud of gas and dust that surrounded the young sun, gradually accumulating into a molten ball of rock and metal that would, over hundreds of millions of years, cool, solidify and develop the atmosphere and surface conditions we recognise today. At some point in that process the Earth acquired its water, and despite more than a century of scientific investigation, no one is entirely certain where that water came from. The numbers are staggering. The world's oceans contain roughly 1.335 billion cubic kilometres of water, covering 361 million square kilometres of surface area to an average depth of about 3,682 metres. Water is, by volume and by mass, one of the dominant features of the planet, and yet, explaining how it got here remains one of the great open questions in planetary science. There are broadly 2 categories of theory, as Dr. Helena Bates, a postdoctoral researcher in meteorite science at the Natural History Museum in London, has explained. The first holds that the Earth formed in a region of the young solar system where water was already present in some form, locked into the minerals and rocks that accreted to form the planet. In this scenario, the water was here from the beginning, trapped inside the growing Earth and gradually released to the surface through volcanic activity over hundreds of millions of years. The second theory holds that the Earth formed in a region of the solar system that was too hot to retain water, and that the water was delivered later, primarily by comets and water-rich asteroids that bombarded the young planet during its first billion years. These objects, originating from colder, more distant regions of the solar system, would have carried ice and hydrated minerals that released water upon impact. Over millions of years of bombardment, enough water accumulated on the surface to form the oceans. Both theories have evidence in their favour. Analysis of ancient volcanic rocks and deep mantle minerals has shown that the Earth's interior contains significant quantities of water, bound up in the crystal structures of minerals like ringwoodite, which is found at depths of several hundred kilometres. This suggests that at least some of the planet's water was incorporated during formation. On the other hand, the chemical composition of ocean water, particularly its ratio of deuterium to hydrogen, has been compared to the water found in various types of asteroids and comets. The best match so far is with a class of asteroids called carbonaceous chondrites, which are rich in water and organic compounds and which originated in the outer asteroid belt. The reality is likely a combination of both sources. Some water was present from the beginning, inherited from the materials that built the planet. Some was delivered later, carried by asteroids and comets during the period of heavy bombardment that scarred the surfaces of the Moon, Mars and Mercury with the craters we can still see today. The relative contribution of each source, how much water was original and how much was imported, is the question that planetary scientists are still trying to answer. What makes this mystery particularly compelling is its scope. We are not asking about a single event or a single location. We are asking about the origin of the most fundamental feature of the planet's surface, the substance that makes life possible, the medium in which every ocean mystery we have discussed tonight exists. Without the water, there is no Mary Celeste, no Mariana Trench, no bloop, no brine pools, no bioluminescence, no Greenland sharks drifting in the dark. The water is the story. And we still do not fully know where it came from. It is in its way the deepest ocean mystery of all, and while planetary scientists debate how the water arrived, the water itself has been quietly developing one of its most spectacular abilities, the ability to glow. Bioluminescence, the production of light by a living organism, is one of the most widespread and least understood phenomena in the ocean. It occurs at every depth, in every ocean, and in an astonishing range of creatures. Jellyfish pulse with blue-green light as they drift through the darkness. Anglerfish dangle glowing lures in front of their jaws to attract prey. Firefly squid found in the waters off Japan produce cascades of electric blue light so intense that the surface of Toyama Bay glows visibly during their annual spawning season. Even some species of shark produce light using photophores along their bellies to match the faint glow filtering down from the surface, a form of camouflage called counterillumination that hides their silhouettes from predators below. The chemistry behind bioluminescence is relatively well understood. It involves a light-producing molecule called luciferin, which reacts with an enzyme called luciferase in the presence of oxygen to produce photons. The reaction is remarkably efficient, generating light with very little heat, which is why it is sometimes called cold light. The specific luciferin and luciferase molecules vary between species, which is part of what makes the phenomenon so scientifically interesting. The machinery for producing light has evolved independently in the ocean at least 100 times, according to current estimates, meaning that dozens of unrelated lineages of marine organisms have separately developed the ability to glow. What makes this number so extraordinary is what it implies about the selective pressure driving the trait. For bioluminescence to have evolved independently 100 times, it must confer an enormous survival advantage, and indeed, in the deep ocean, where sunlight never penetrates and the only illumination comes from living things, the ability to produce, control, and respond to light is a matter of life and death. Estimates suggest that as many as 90% of animals living in the ocean's twilight zone, the layer between 200 and 1,000 meters, where the last traces of sunlight fade into total darkness, may produce light in some form. It is not the exception down there, it is the rule. The uses are as varied as the creatures that employ them. Some animals use light to attract mates in the absolute blackness. Others use it to lure prey, dangling luminescent appendages in front of their mouths like fishing lures. Some species produce sudden blinding flashes to startle and confuse predators, a tactic called the burglar alarm hypothesis, since the flash can attract even larger predators that may attack the original threat. And some creatures use bioluminescence in ways that researchers are only beginning to understand. Professor John Copley, a marine ecologist at the University of Southampton, has noted that one of his favourite examples is the lantern shark, which uses bioluminescent markings on its body to advertise the sharp, unappetizing spines along its back, essentially creating a glowing warning label that tells would-be predators to look elsewhere. In 2024, a study led by Dr. Danielle DeLeo of Florida International University traced the evolutionary origins of bioluminescence in a group of marine invertebrates, providing new data on when and how the trait first emerged. The research added to a growing body of evidence suggesting that bioluminescence is far more ancient and far more central to ocean ecology than previously realized. But despite these advances, fundamental questions remain. Why did bioluminescence evolve so many times independently? What are all the specific functions it serves in the hundreds of species that possess it? And why is it so overwhelmingly concentrated in the ocean, with far fewer examples on land? The deep ocean is a world lit by its own inhabitants. Every flash, every glow, every sustained luminescence is a message, a warning, a lure, or a signal, broadcast into the darkness by creatures that have spent millions of years perfecting the art of making light where none exists. It is a language we are only beginning to learn to read. And if the deep ocean communicates in light, the surface of the Pacific has its own language, one spoken in disappearances. South of Tokyo, in the western Pacific Ocean, lies a stretch of water that has earned a reputation eerily similar to the Bermuda Triangle. Japanese sailors call it the Ma no Umi, the Sea of the Devil. Western writers have dubbed it the Dragon's Triangle. It encompasses a broad area of the Philippine Sea between Japan and the Northern Mariana Islands, and like the Bermuda Triangle, it has been associated with the unexplained disappearance of ships, aircraft, and in some accounts, entire military vessels. The legends surrounding the Dragon's Triangle are older than those of the Bermuda Triangle by centuries. Japanese folklore includes stories of sea dragons that dwell in the depths, pulling ships beneath the waves. Fishermen in the region have long regarded certain areas as cursed or haunted, places where the sea behaves unpredictably and where boats that enter do not always return. These stories were, for most of their history, treated as myth, but in the modern era, a series of documented incidents gave the myths a harder edge. In the early 1950s, the Japanese government reportedly lost several fishing boats in the area, under circumstances that were never fully explained. In 1952, the Japanese research vessel Kayomaru No. 5 was dispatched to investigate the disappearances. The ship, carrying a crew of 31 scientists and sailors, vanished in the Dragon's Triangle and was never found. According to some accounts, the Japanese government subsequently declared the area a danger zone, though the details and the official status of this declaration have been debated by historians. The scientific explanation for the unusual number of maritime incidents in the Dragon's Triangle is less exotic than the legends suggest. The region sits squarely within the Pacific Ring of Fire, one of the most geologically active zones on the planet. Underwater volcanic eruptions, some of them large enough to generate sudden changes in sea level, gas releases, and even new islands, are not uncommon. The Havre volcano, which lies 3,000 feet below the surface in the Pacific, produced the largest deep-water volcanic eruption ever recorded when it erupted in 2012. Eruptions like these can create sudden hazards for ships, including superheated water, toxic gas emissions, floating fields of pumice, and rapid, unpredictable changes in water depth. In addition to volcanic activity, the region is subject to powerful ocean currents, including the Kuroshio Current, one of the strongest western boundary currents in the world. The Kuroshio can generate dangerous eddies, standing waves, and sudden shifts in water temperature that create dense fog and reduce visibility to near zero. Typhoons are also common in the area, and the combination of warm water, strong currents, and frequent storms makes navigation inherently more dangerous than in calmer regions. The Dragon's Triangle, like the Bermuda Triangle, is also a heavily travelled maritime corridor, with shipping routes connecting Japan to Southeast Asia, Australia, and the South Pacific passing directly through it. The high volume of traffic means that the raw number of incidents is naturally higher than in less travelled waters. Whether the rate of incidents per vessel is actually elevated above normal statistical expectations is a question that has never been conclusively answered, partly because the data on historical losses in the area is incomplete, and partly because the region's boundaries have never been officially defined. What remains true is that the Western Pacific is one of the most dynamic and geologically active stretches of ocean on the planet, and that the forces operating beneath its surface, volcanic, tectonic, and hydrological, are powerful enough to create hazards that even modern navigation technology cannot always anticipate. The Dragon's Triangle may not be cursed, but it is genuinely dangerous, and the ocean does not distinguish between the two. From the oldest mysteries of the ocean to its newest discoveries, the next story takes us to a stretch of water off the coast of South America, where, in early 2024, the ocean reminded us just how little we actually know about what lies in its depths. In January and February of 2024, a deep-sea research expedition funded by the Schmidt Ocean Institute set out to explore the waters off the coast of Chile in the southeastern Pacific. The region had been identified as a biodiversity hotspot, an area where cold, nutrient-rich currents rising from the deep ocean support an unusually dense and varied ecosystem. But the sheer scale of what the expedition found exceeded even the most optimistic predictions. Over the course of several weeks, using remotely operated vehicles equipped with high-definition cameras and collection tools, the team catalogued more than 100 previously unknown marine species. The discoveries included new species of deep-sea corals, sponges, crustaceans, mollusks, and fish, many of them found at depth below 3,000 meters in environments of total darkness, near freezing temperatures and crushing pressure. Some of the organisms displayed adaptations that researchers had never seen before, including novel bioluminescent patterns, unusual body structures, and behaviors that defied easy categorization. The expedition was part of a broader effort to survey the deep oceans before human activities, including deep-sea mining, bottom trawling, and climate change, alter these ecosystems beyond recognition. Scientists have estimated that as many as 90% of marine species remain undiscovered, a number that the 2024 Chile expedition seemed to confirm. In a single research cruise in a single stretch of water, more than 100 new forms of life were documented. Extrapolate that across the hundreds of millions of square kilometers of unexplored ocean floor, and the scale of what we have not yet found becomes almost incomprehensible. The discovery also highlighted a growing tension in ocean science. Deep-sea ecosystems are increasingly threatened by industrial exploitation, particularly deep-sea mining, which targets mineral deposits on the ocean floor for use in electronics, batteries, and other technologies. The International Seabed Authority, the United Nations body responsible for regulating mining in international waters, has been under pressure from both industry and environmental groups to either approve or ban commercial deep-sea mining. The 2024 Chile expedition added urgency to the conservation argument by demonstrating that the areas proposed for mining may contain species that have not yet been identified, let alone studied. The ocean is not a static place. It is not a museum. It is a living system that is still producing new discoveries at a rate that outpaces our ability to catalogue them. Every time a camera descends to a depth that has not been surveyed before, it finds something we did not know was there, and every one of those discoveries raises the same question. If this is what we find in the places we have looked, what is waiting in the places we have not? The 2024 Chile expedition found over 100 new species in a single stretch of water. The ocean covers more than 360 million square kilometers. The map is humbling. And while new species emerge from the deep, the technology we use to find them is revealing something equally startling about the ocean floor itself. Not what lives on it, but what it looks like. Because as it turns out, most of it is still a blank spot on the map. If you have ever looked at a map of the ocean, you might assume that we know what the bottom looks like. After all, the maps show mountain ranges, trenches, ridges and plains with what appears to be impressive detail. Satellite imagery covers the entire planet. Global positioning systems can fix a location on the surface of the ocean to within a few meters. Surely with all of this technology, we have a clear picture of the terrain beneath the waves. We do not. The maps of the ocean floor that most people have seen are derived from satellite altimetry, a technique that measures the subtle variations in the height of the sea surface caused by the gravitational pull of underwater features. A large seamount, for example, has enough mass to slightly raise the water level above it, and a trench causes a slight depression. By measuring these variations from orbit, scientists can infer the general shape of the seafloor, but the resolution is extremely coarse. Satellite-derived maps can detect features that are about a mile or more across, but anything smaller is invisible. An entire shipwreck could be sitting on the bottom, and satellite maps would never show it. A volcanic vent, a brine pool, a coral reef, a field of manganese nodules, all of these would be completely absent. High resolution in mapping of the ocean floor requires direct acoustic measurement, typically using multi-beam sonar mounted on the hull of a research vessel. The sonar sends a fan of sound pulses toward the seafloor and measures the time it takes for the echoes to return. By processing these echoes, the system builds a detailed three-dimensional picture of the terrain below. The resolution is incomparably better than satellite data, capable of revealing features as small as a few meters across. But there is a catch. To map the ocean floor with multi-beam sonar, you have to physically sail a ship over every square kilometer you want to survey. And the ocean is enormous. As of June 2024, according to the Seabed 2030 project, only about 26.1% of the global ocean floor had been mapped with modern high-resolution sonar technology. That number has been climbing steadily. When the project was launched in 2017, less than 6% had been mapped. But even at the current pace of progress, achieving complete coverage by the project's 2030 target date is ambitious to the point of improbability. The remaining 74% represents an area of more than 260 million square kilometers, roughly the combined land area of every continent on Earth multiplied by nearly 2. What might be hiding in that unmapped 74% is a question that keeps ocean scientists awake at night. Seamounts, underwater mountains that rise thousands of meters from the seafloor but do not break the surface, are almost certainly present in the unmapped zones in large numbers. Current estimates suggest there may be more than 100,000 seamounts in the ocean, but only a fraction have been charted. Each one is a potential hotspot of biodiversity, supporting ecosystems that have evolved in isolation on their rocky flanks. Undiscovered hydrothermal vents, brine pools, mineral deposits, and geological formations of types we may not even have categories for could exist in the vast blank spaces of the ocean floor map. And then there are the shipwrecks. The United Nations Educational, Scientific and Cultural Organization, UNESCO, estimates that there are approximately 3 million shipwrecks scattered across the world's ocean floors. The vast majority have never been located. Some are centuries old. The remains of exploration-era galleons, warships from forgotten conflicts, and merchant vessels lost to storms and navigation, errors in an age before radio. Others are modern, submarines and cargo ships and fishing boats that went down in deep water and were never recovered. Each one is a time capsule, a snapshot of the moment it sank, preserved by the cold, lightless, oxygen-poor conditions of the deep sea. The ocean floor is not empty, it is simply unseen, and the effort to change that, to fill in the blank spaces on the map and reveal what lies beneath, is one of the most ambitious scientific undertakings in history. But until it is complete, the majority of the Earth's surface remains in a very real sense terra incognita, and sometimes the ocean reveals its hidden features not through patient mapping, but through sudden violent eruption. In July 2012, passengers aboard a commercial aircraft flying over the South Pacific noticed something unusual in the water below. A vast irregular raft of grey pumice, volcanic rock so porous that it floats, was drifting on the surface of the ocean. The raft stretched for miles, covering an area comparable to a small city. It looked, from the air, like a highway of stone laid across the blue water. The pumice had come from the Havre volcano, a submarine volcano located on the Kermadec volcanic arc, roughly 600 miles northeast of New Zealand. The Havre sits about 900 metres below the surface, deep enough that its eruption was almost entirely invisible from above. There was no ash cloud, no explosive column of steam and gas breaking the surface, no tsunami warning. The only evidence that anything had happened was the pumice raft, which was first noticed by airline passengers and then confirmed by satellite imagery. It was the largest deep-water volcanic eruption ever documented. When scientists eventually descended to the Havre in 2015 using remotely operated vehicles, they found a dramatically altered landscape. The eruption had produced more than a cubic kilometre of material, blasting pumice and lava across the seafloor in a debris field that covered an area of more than 40 square kilometres. Giant blocks of pumice, some the size of vans, were scattered across the terrain. New lava flows had buried older features of the volcano, and the shape of the summit had been significantly changed. The researchers found that the eruption had been far larger and more complex than anyone had anticipated, involving multiple eruptive styles and producing material over a period of several hours or days. The Havre eruption highlighted a critical gap in our understanding of submarine volcanism. There are thousands of active or potentially active volcanoes beneath the ocean surface, most of them along the mid-ocean ridges and subduction zones that define the boundaries of tectonic plates. The vast majority have never been monitored, many have never been surveyed. The Havre eruption was only detected because it was large enough to produce a visible pumice raft on the surface. Smaller eruptions, which are far more common, can occur and conclude without anyone ever knowing they happened. The implications are significant. Submarine eruptions can produce underwater landslides, which in turn can generate tsunamis. They can release enormous quantities of gas into the water, altering local chemistry and potentially affecting marine life over wide areas. They can create new islands, destroy existing ones, and reshape the seafloor in ways that affect ocean currents and navigation. And they are happening all the time, in places where no one is watching. The ocean does not always announce its dramas. Sometimes the most powerful events on the planet unfold entirely beneath the surface, and the only evidence we find is a field of floating stone and a changed landscape on the bottom. From hidden volcanoes to hidden histories, the floor of the Gulf of Mexico holds more stories than almost any other stretch of seabed on the planet. And many of those stories have never been read. The Gulf of Mexico is one of the most intensively used bodies of water in the Western Hemisphere. Oil platforms, shipping lanes, fishing grounds, and military testing ranges cover its surface. But beneath that surface lies an archaeological treasure trove of staggering proportions. It is estimated that more than 4,000 shipwrecks rest on the floor of the Gulf, spanning a period from the earliest European exploration of the Americas to the modern era. The vast majority have never been identified. The wrecks include Spanish galleons from the colonial era, some of them carrying gold, silver, and precious stones from the mines of Mexico and South America. They include Confederate blockade runners from the Civil War, Union warships and German U-boats from both world wars, They include fishing boats, cargo vessels, tankers and pleasure craft that went down in hurricanes, collisions, fires and mechanical failures over the course of 5 centuries. Each one is a piece of history sitting in the dark, slowly being buried by sediment and colonized by marine life. In 2019, a particularly intriguing discovery was made during a routine survey of the Gulf floor. Sonar technology detected the remains of an unknown ship at a depth of several thousand feet. When remotely operated vehicles were sent to investigate, they revealed a 124-foot-long wooden vessel with copper sheathing on its hull, a construction technique common in the 19th century. The ship's structure was remarkably well preserved by the cold, low oxygen conditions at the bottom of the Gulf. Its masts were gone, collapsed under the weight of time and water, but the hull was largely intact, and artifacts were visible on and around the wreck site. As of the most recent reports, the identity of the ship has not been established. Researchers do not know what country it sailed from, what it was carrying, how many crew were aboard, or what caused it to sink. The copper sheathing and construction style suggest a mid to late 19th century origin, possibly a merchant vessel or a naval supply ship. But without identifying markings, a ship's bell, or recoverable documentation, the wreck remains anonymous, one more unnamed entry in the Gulf's long ledger of lost ships. The Gulf of Mexico is in a sense a museum without labels. Thousands of wrecks lie scattered across its floor, each one a frozen moment in time, each one carrying a story that has been locked in silence since the day the water closed over it. A few have been identified and studied. The vast majority have not. And every hurricane season, every shift in the seafloor, every tremor of the Earth's crust adds new entries to the collection. The ocean is not just a graveyard of ships, it is an archive, and most of its records have never been opened. But the Gulf's wrecks, as fascinating as they are, exist in relatively shallow, accessible water. The deepest, strangest and most alien places in the ocean lie far beyond the reach of any wreck, at the boundary between geology and biology, where the Earth's crust splits open and the ocean fills with fire. In 1977, a team of geologists aboard the research vessel Canoe, operated by the Woods Hole Oceanographic Institution, was exploring the seafloor near the Galapagos Islands in the eastern Pacific. They were looking for evidence of hydrothermal activity, places where superheated water might be seeping from cracks in the Earth's crust along the mid-Atlantic ridge's Pacific counterpart, the East Pacific Rise. Theoretical models predicted that such vents should exist, but no one had ever seen one. The team lowered a deep-sea camera system called Angus, a towed sled equipped with cameras and temperature sensors, to a depth of roughly 2,500 meters and began photographing the ocean floor. What they found changed biology forever. The cameras returned images of a landscape that looked like something from another planet. Towers of mineral deposits, some of them several meters tall, rose from the seafloor, belching plumes of superheated mineral-laden water into the frigid deep. The water emerging from the vents was shimmering with dissolved chemicals, primarily hydrogen sulfide, and at temperatures exceeding 350 degrees Celsius, hot enough to melt lead. Yet surrounding these chimneys, in water that should have been sterile and lifeless, was an ecosystem of staggering abundance. Giant tube worms, some over 2 meters long, clustered around the vents in dense thickets, their bright red plumes waving in the current. Mats of white bacteria carpeted the surrounding rock. Clams the size of dinner plates nestled in the crevices. Shrimp, crabs and strange pale fish moved through the scene in numbers that defied every expectation about life in the deep ocean. The discovery was revolutionary for one fundamental reason. Every ecosystem previously known to science ultimately depended on sunlight. Plants on land and phytoplankton in the ocean convert solar energy into chemical energy through photosynthesis. And every other organism in the food chain depends, directly or indirectly, on that conversion. But at the bottom of the ocean, thousands of meters below the reach of any sunlight, the hydrothermal vent ecosystems had found a different way. The bacteria that formed the base of the food chain around the vents were chemosynthetic, meaning they derived their energy not from light, but from the chemical reactions between the hydrogen sulfide pouring out of the vents and the oxygen dissolved in the surrounding seawater. The tube worms had no mouths and no digestive systems at all. Instead, they harboured billions of chemosynthetic bacteria inside their bodies in a specialised organ called a trophosome, and the bacteria provided all the nutrition the worms needed. It was, in essence, an entirely alien model for life. An ecosystem powered not by the sun but by the heat and chemistry of the Earth's interior. And it raised a question that has driven astrobiology ever since. If life can thrive in total darkness, at crushing pressures in water laced with chemicals that would kill most surface organisms, then where else in the universe might similar conditions support life? The answer, many scientists believe, is on the ocean moons of the outer solar system. Jupiter's moon Europa and Saturn's moon Enceladus are both believed to harbour liquid water, oceans beneath their icy surfaces, kept warm by tidal heating from the gravitational pull of their parent planets. If hydrothermal vents exist on the floors of those oceans, and there is circumstantial evidence to suggest they might, then the same chemical energy that powers the vent ecosystems on Earth could, in theory, power ecosystems on those worlds. The discovery of hydrothermal vents on Earth transformed the search for extraterrestrial life from a matter of science fiction into a matter of science. Since 1977, hundreds of hydrothermal vent fields have been discovered along mid-ocean ridges, back-arc basins, and volcanic arcs around the world. Each one supports its own community of organisms, many of them found nowhere else. The species composition varies from vent to vent and from ocean to ocean, but the basic model is the same. Chemical energy from the Earth's interior, converted by bacteria into biological energy, supporting food chains that exist in complete independence from the sun. The vents themselves are classified into two main types based on their temperature and chemistry. Black smokers are the hottest and most dramatic, producing plumes of superheated water that precipitate dark clouds of mineral particles, primarily iron and sulfide compounds. As they mix with the cold surrounding water, the mineral particles settle around the vent opening and gradually build the chimney structures that give black smokers their iconic appearance. Some chimneys grow to enormous sizes. The tallest ever recorded a structure in the Atlantic named Godzilla reached a height of more than 45 meters before it collapsed under its own weight. White smokers are cooler, typically venting water at temperatures between 200 and 300 degrees Celsius, and they produce lighter coloured plumes containing compounds like barium, calcium, and silicon. The ecosystems around white smokers tend to be somewhat less productive than those around black smokers, but they are still remarkably rich compared to the surrounding deep-sea floor, which is often described as a biological desert. One of the most remarkable features of vent ecosystems is their impermanence. Individual vent sites are geologically short-lived, typically active for only a few decades to a few centuries before the underlying plumbing shifts and the flow of heated water stops. When a vent dies, the ecosystem it supported collapses. The tube worms die, the bacterial mats wither, the crabs and shrimp move on or perish. Within a few years, a site that was once teeming with life becomes a cold, barren field of mineral chimneys, slowly crumbling back into the seafloor. Yet somehow, vent organisms persist. When a new vent opens, sometimes miles from the nearest active site, it is colonized within months or years by the same types of organisms that populated the old one. How the larvae of these creatures find new vents in the vast dark ocean, navigating across miles of barren seafloor to reach a tiny newly opened crack in the crust, is a question that remains only partially answered. Some researchers believe the larvae can detect chemical gradients in the water, following the faintest trace of hydrogen sulfide like a scent trail through the darkness. Others think the process is largely random, with billions of larvae dispersing across the ocean and a few lucky ones landing in the right place at the right time. Either way, the result is the same. Life at the bottom of the ocean is not a static, fixed thing. It is dynamic, opportunistic and resilient in ways that continually surprise the scientists who study it. The vents are born and die on a human timescale, but the ecosystems they support have been cycling through creation and destruction for hundreds of millions of years, long before the first fish swam or the first animal crawled onto land. Hydrothermal vents are a reminder that the Earth is not a passive stage on which life performs. It is an active participant, generating the energy and the chemistry that life exploits, constantly reshaping the conditions at the bottom of the ocean, and in doing so constantly reshaping the possibilities for what can survive there. And if the vents represent life at its most extreme and most innovative, there is one creature in the ocean that represents life at its most enduring. An animal so ancient that it predates nearly everything else alive on the planet. A living fossil in the truest sense of the phrase. The Nautilus is a cephalopod, a member of the same broad family that includes octopuses, squid, and cuttlefish. But unlike its soft-bodied relatives, the Nautilus lives inside a hard, spiraling shell, divided into chambers that the animal fills with gas and liquid to control its buoyancy. The shell is beautiful, a logarithmic spiral of pearly white and reddish brown that has inspired artists, mathematicians, and architects for centuries. But the Nautilus is far more than a pretty shell. It is one of the oldest surviving animal lineages on Earth. The Nautilus genus, Nautilus, belongs to a broader group called the Nautiloids, which first appeared in the fossil record during the late Cambrian period, more than 480 million years ago. To put that number in context, the Nautiloids were already ancient by the time the first fish evolved. They were swimming in the oceans before the first plants colonized the land. They survived the Ordovician, Silurian extinction, which wiped out roughly 85% of marine species about 445 million years ago. They survived the late Devonian extinction, the Permian-Triassic extinction, which was the worst mass extinction in Earth's history, killing more than 95% of all marine species about 252 million years ago. They survived the Triassic-Jurassic extinction. They survived the Cretaceous-Paleogene extinction that ended the age of the dinosaurs 66 million years ago. They are still here. The modern Nautilus species, of which there are a handful, are found in the deep waters of the Indo-Pacific, typically between 100 and 300 meters in depth, along the steep outer slopes of coral reefs and continental shelves. They are nocturnal, rising from the deep at night to feed on small crustaceans, fish and carrion, then retreating to the darkness during the day. They have poor eyesight, relying instead on their highly developed sense of smell to locate food. They move by jet propulsion, drawing water into their mantle cavity and expelling it through a siphon, the same basic mechanism used by squid and octopuses, but executed with considerably less speed and agility. The Nautilus is not a fast animal. It does not need to be. It has survived for nearly 500 million years by being durable, efficient, and adaptable, not by being fast. The shell itself is a masterpiece of natural engineering. As the Nautilus grows, it constructs new larger chambers at the opening of the shell and seals off the old ones behind it. The sealed chambers are connected by a thin tube called a siphuncle, through which the Nautilus can regulate the ratio of gas and liquid in each chamber, adjusting its buoyancy with remarkable precision. This allows the animal to rise and sink in the water column without expending energy, a trick that modern submarines achieve with ballast tanks and that the Nautilus perfected hundreds of millions of years before humans existed. Despite their extraordinary longevity as a lineage, modern Nautilus populations are under significant threat. The shells are highly valued in the international jewellery and souvenir trade, and overharvesting has reduced populations in several regions. Unlike most cephalopods, Nautiluses grow slowly and reproduce infrequently, making them particularly vulnerable to overfishing. In 2016, the entire genus Nautilus was listed under Appendix 2 of the Convention on International Trade in Endangered Species, CITES, in an effort to regulate the shell trade and prevent further population declines. It is a strange and bitter irony. an animal that has survived every catastrophe the planet has thrown at it for nearly 500 million years, that outlasted the dinosaurs and the ice ages and the asteroid impacts and the volcanic winters, is now threatened by the one force it was never designed to withstand. Us. The Nautilus drifts through the deep Indo-Pacific on the same currents it has ridden since before the age of reptiles, enclosed in a shell that is both its home and its history. Each chamber records a chapter of growth. Each spiral traces a mathematical curve that nature has been drawing for longer than most mountains have existed. It is a living archive of deep time, and it is running out of time of its own. From the oldest living animal to the newest discoveries, from the fires of the deep to the silence of ghost ships, the ocean has shown us tonight that it operates on scales that dwarf human comprehension. And yet we keep looking, we keep descending, we keep listening, because the ocean, for all its vastness and all its danger, is the closest thing we have to another world. And the urge to explore it is the same urge that has driven every voyage, every dive, and every question we have ever asked about the dark water below. But before we reach the end of this journey, the ocean has more to show us. Phenomena that blur the line between the explainable and the uncanny. Forces that even experienced sailors once refused to believe were real. And one of those forces, for centuries, was dismissed as nothing more than a tall tale. Rogue waves, monster waves, freak waves. The names themselves sound like fiction. The kind of stories old sailors told over rum to frighten younger crew members. For most of recorded maritime history, the idea that a single isolated wave could rise to a height of 80, 90, or even 100 feet in otherwise moderate seas was considered impossible by mainstream science. Oceanographers modelled wave behaviour using statistical methods, and those models predicted that waves of extreme height should occur so rarely as to be essentially non-existent in any practical time frame. A wave twice the height of the surrounding sea state was theoretically possible, but vanishingly unlikely. A wave 3 times the surrounding height was treated as a mathematical abstraction, not a real-world phenomenon. Sailors knew better. For centuries, mariners had reported encounters with walls of water that appeared without warning, rising from the surface of the ocean as though the sea itself had reared up on its hind legs. Ships returned to port with twisted steel, smashed superstructures, and crews that spoke of being hit by waves that towered over their masts. Some ships did not return at all. The accounts were vivid, specific, and consistent across cultures and centuries, but without instrumental evidence, the scientific establishment largely dismissed them. That changed on January 1st, 1995. On New Year's Day, an oil platform called the Drapner E operated in the North Sea off the coast of Norway, recorded a wave that would rewrite the textbook on ocean dynamics. The platform was equipped with a laser-based wave measurement system, an instrument that bounced a beam of light off the surface of the water and measured the distance to calculate wave height with high precision. On that stormy afternoon, the instrument registered a single wave measuring 25.6 meters in height, approximately 84 feet. The significant wave height at the time, meaning the average of the tallest third of the waves in the area, was about 12 meters. The Drapner wave was more than twice the height of the surrounding sea state. It was the first scientifically measured rogue wave, and it proved that what sailors had been describing for centuries was real. Since the Drapner event, rogue waves have been measured and documented multiple times by ocean buoys, satellite radar, and ship-mounted instruments. The emerging picture is sobering. Rogue waves are not as rare as classical wave theory predicted. They can form through several mechanisms, including constructive interference, where multiple wave systems travelling in different directions converge at a single point, and their energies combine to produce a wave of extraordinary height, and through interactions between waves and strong ocean currents, particularly in areas where currents flow in the opposite direction to the prevailing waves, compressing wave energy into a smaller space and forcing it upward. The areas most prone to rogue waves are also some of the most heavily travelled shipping corridors in the world. The Agulhas Current off the coast of South Africa, where warm water flowing south meets cold Antarctic currents flowing north, is notorious for producing rogue waves. The North Sea, the Northwest Pacific, and the waters around Cape Horn at the southern tip of South America are also hotspots. In these regions, the interaction between strong currents and storm-generated waves creates the conditions for rogue wave formation on a regular basis. The damage caused by rogue waves is not theoretical. In February 1995, just weeks after the Draupner measurement, the cruise ship Queen Elizabeth II was struck by a rogue wave in the North Atlantic that her captain described as a wall of water that seemed to come from nowhere. He estimated the wave at approximately 90 feet. In 2001, two cruise ships, the Bremen and the Caledonian Star, were hit by rogue waves in the South Atlantic within a week of each other. Both ships lost power and bridge windows. In 2005, the cruise ship Norwegian Dawn was struck by a 70-foot wave off the coast of the Carolinas that damaged cabins on the upper decks and injured several passengers. How many ships have been sunk by rogue waves without anyone surviving to report the encounter is a question that cannot be answered, but maritime historians suspect the number is significant. Before the Draupner measurement, any captain who reported being sunk by a single monster wave would have been dismissed. After Draupner, those reports were taken seriously, and a number of previously unexplained sinkings were re-evaluated in light of the new understanding. Rogue waves are no longer a mystery in the sense that their existence is questioned. They are real, they are measurable, and they are more common than anyone expected. But they remain a mystery in the sense that predicting when and where they will form is still beyond the reach of current science. A ship sailing through moderate seas has no way of knowing that a rogue wave is building until it is already upon them. The ocean surface can go from orderly to catastrophic in a matter of seconds, and then return to calm as though nothing happened. It is one of the ocean's most unsettling qualities. Not that it is dangerous, every sailor knows that, but that the danger can appear instantaneously, without warning, and then vanish just as quickly. The ocean does not telegraph its worst, it simply delivers. And if the ocean's physical power can manifest without warning, its biological world can produce sounds so singular, so isolated, that they haunt the scientists who study them. One of those sounds has been called the loneliest voice in the ocean. In 1989, a team of researchers at the Woods Hole Oceanographic Institution detected an unusual whale call in the North Pacific. The call was similar in pattern and timing to those of blue whales and fin whales, the two largest species on the planet, both of which communicate across vast distances using extremely low frequency sounds. But this call was different. It was broadcast at a frequency of approximately 52 Hz. That number may not sound significant until you understand the context. Blue whales typically vocalize at frequencies between 10 and 39 Hz. Fin whales call at around 20 Hz. The 52 Hz signal was well above the range used by either species. It was as though someone was speaking in a language that was recognizable in structure but incomprehensible in pitch, and it appeared to be coming from a single animal, one individual whale, calling across the Pacific at a frequency that no other whale could match. The signal was first identified by William Watkins, an acoustics researcher at Woods Hole, who had spent decades studying whale vocalizations. Watkins and his team tracked the 52 Hz call over the following years using recordings from the Navy's SOSUS network, the same hydrophone array that had detected the bloop. The call followed a migration pattern consistent with a large baleen whale, travelling north in the summer and south in the winter, but it was always alone. In every recording, across every season and every year, the 52 Hz signal came from a solitary source. There was never a response. Watkins published a paper on the signal in 2004, shortly before his death, and the story quickly captured public attention. The media dubbed the animal the 52 Hz whale, and later, the world's loneliest whale. The idea of a whale calling out across the vast emptiness of the Pacific, year after year, never hearing an answer, resonated deeply with people. A documentary film, The Loneliest Whale, The Search for 52, was released in 2021, following a team of researchers who attempted to locate and identify the animal using modern acoustic tracking technology. Scientists are cautious about the loneliness narrative. It is possible that the 52 Hertz whale is a hybrid between two species, perhaps a blue whale and a fin whale, producing calls at an intermediate frequency. Hybridization between these two species has been documented. It is also possible that the whale has a physical abnormality that raises its vocal pitch, and crucially, there is no evidence that the animal is distressed or isolated in the way that the popular story implies. Whales communicate across vast distances, and the absence of a detected response does not necessarily mean the call goes unheard. Other whales may hear the 52 Hertz signal and simply not respond at that frequency. But the appeal of the story is not really about the science, it is about the image. A single voice in the darkness of the Pacific, calling out at a pitch that no one else uses, following its ancient migratory path alone, year after year, through waters that stretch for thousands of miles in every direction. Whether or not the whale is truly lonely in any way it can feel or understand, the image is indelible, and it speaks to something about the ocean itself, the way it can reduce even the largest animals on Earth to solitary specks in a vastness that swallows everything. The 52 Hertz whale has been tracked on and off for more than 3 decades. As of the most recent recordings, it is still out there, still calling, still moving through the Pacific on its solitary route, and still, as far as anyone can tell, getting no answer. And while the 52 Hertz whale represents one of the ocean's most poignant biological puzzles, the deep ocean presents another that is far more visceral, because in the crushing pressures and eternal darkness of the abyss, something strange happens to the creatures that live there. They grow. They grow far larger than their shallow water relatives, and nobody is entirely sure why. Deep-sea gigantism is the term scientists use to describe the observed tendency for deep-water species to grow significantly larger than their counterparts in shallower water. Examples are found across the animal kingdom. The Japanese spider crab, found at depths of up to 600 meters, has a leg span that can exceed 12 feet, making it the largest living arthropod. The giant isopod, a relative of the common woodlouse, grows to more than 16 inches long in the deep ocean, roughly 30 times the size of its terrestrial cousin. Oarfish, long, ribbon-shaped creatures that inhabit the mesopelagic zone can reach lengths of over 30 feet, and the giant squid, the ocean's most iconic deep-water mystery, can grow to at least 43 feet in total length, with tentacles that account for much of that span, making it one of the largest invertebrates ever to have lived. The colossal squid, a separate species found in the deep Southern Ocean, may be even heavier than the giant squid, though it is thought to be somewhat shorter. Specimens recovered from the stomachs of sperm whales have included beaks and tentacle fragments suggesting animals of enormous proportions. In 2007, a live colossal squid was captured by a New Zealand fishing vessel in the Ross Sea. It measured approximately 33 feet long and weighed over 1,000 pounds, but researchers believe it was not fully grown. Several hypotheses have been proposed to explain deep-sea gigantism. One is Bergmann's rule, which observes that animals in colder environments tend to be larger because a larger body has a smaller surface area to volume ratio, reducing heat loss. The deep ocean is cold, typically between 1 and 4 degrees Celsius, and larger bodies would conserve heat more efficiently. Another hypothesis relates to the availability of oxygen. The deep ocean, while cold, often contains higher concentrations of dissolved oxygen than warmer surface waters, and greater oxygen availability could support the metabolic demands of a larger body. A third hypothesis, and perhaps the most intriguing, is related to the absence of predators. In the deep ocean, far from the predator-rich waters of the continental shelves, the selective pressure to remain small and inconspicuous is reduced. Animals can afford to grow larger because there are fewer threats capable of eating them, and in an environment where food is scarce and arrives unpredictably, a larger body can store more energy, allowing the animal to survive longer between meals. None of these hypotheses fully explains the phenomenon, and it is likely that deep-sea gigantism is the result of multiple interacting factors rather than a single cause. But the result is a deep ocean populated by creatures that seem scaled up from their shallow water relatives, living in slow motion in the cold and dark, growing to sizes that would be impossible closer to the surface. The deep ocean is not just another environment. It is a different world, governed by different rules, producing different outcomes. And the creatures that live there are a constant reminder that the ocean's capacity for strangeness has no obvious limit. From monster waves to loneliest whales, from deep-sea giants to invisible volcanoes, the ocean keeps delivering evidence that its mysteries are not relics of the past. They are ongoing, they are accumulating, and they are, if anything, deepening as our tools grow sharper and our reach extends farther into the dark. There is one ghost ship story that circulates through the darker corners of maritime history with a persistence that no amount of debunking seems to kill. It is the story of the SS Orang Medan, a ship whose crew, according to the legend, did not vanish. They died, all of them, at the same time, with looks of absolute terror frozen on their faces. The story goes like this. In June of 1947, or possibly 1948, depending on which version you encounter, multiple ships traversing the Strait of Malacca between Sumatra and Malaysia picked up a distress signal. The message, transmitted in Morse code, reportedly read, "All officers including captain are dead, lying in chart room and bridge, possibly whole crew dead." After a pause, the transmission continued with a few garbled, indecipherable words, and then a final chilling addendum. "I die." After that silence, an American merchant vessel, the Silver Star, responded to the distress call and located the Orang Medan drifting in the strait. When a boarding party crossed over, they found a scene out of a nightmare. The entire crew was dead, scattered across the decks, the bridge, and the chart room. Their eyes were open. Their arms were outstretched as though reaching for something or trying to ward something off. Their faces were contorted in expressions of terror. Even the ship's dog was dead, frozen mid-snarl. There were no visible injuries on any of the bodies, no wounds, no blood, no signs of struggle or violence, and the boarding party reported that despite the tropical heat of the Strait of Malacca, the air aboard the Orang Medan was inexplicably cold. Before the Silver Star could take the ship in tow, a fire broke out in the number 4 hold. The boarding party evacuated immediately. Minutes later, the Orang Medan exploded and sank, taking the bodies, the ship, and whatever evidence might have explained the deaths to the bottom of the strait. The story is terrifying. It is also almost certainly not true, or at least not true in the way it is usually told. Researchers who have attempted to verify the account have found no official record of a ship named Orang Medan in any maritime registry. Lloyd's of London, the most comprehensive insurer and record keeper of global shipping, has no listing for the vessel. No newspaper accounts from 1947 or 1948 have been found in the region that corroborate the distress signal or the discovery. The Silver Star's logs, to the extent they have been examined, do not appear to contain an entry about the incident. The earliest known published account of the Orang Medan story appeared in a 1948 Dutch-Indonesian newspaper, and it was subsequently picked up and embellished by other publications over the following decades. The details shifted with each retelling. The date changed, the location changed, the number of dead varied, the story accumulated dramatic details, the frozen expressions, the cold air, the spontaneous explosion that have the unmistakable fingerprints of a tale that has been improved by each teller. Some researchers have suggested that the Orang Medan may have been a smuggling vessel carrying an illicit cargo of potassium cyanide or nitroglycerin, chemicals that could have released toxic gases and killed the crew through asphyxiation. In this scenario, the lack of a registry listing would be expected, since smuggling ships often operated under false names or without proper documentation. The fire and explosion could have been caused by the unstable cargo, and the terrified expressions on the crew's faces could be consistent with death by cyanide poisoning, which causes convulsions and involuntary muscle contractions. Others believe the entire story is a fabrication, a piece of maritime folklore that was invented, or at least heavily embroidered, by the newspaper that first published it, and that it has since been passed from book to book and website to website without anyone ever locating the original evidence. The Orang Medan occupies a strange place in the catalogue of ocean mysteries. It is famous, widely cited, and deeply unsettling. It is also almost completely unverifiable. The ocean in this case may not be hiding a mystery at all. It may simply be providing the setting for one that never happened. But whether the Orang Medan is fact or fiction, the ocean is accumulating a very real crisis that requires no legend to be frightening. And this one is not hidden in the deep or lost in the past. It is floating on the surface, in plain sight, growing larger every year. The Great Pacific Garbage Patch is not, despite its name, a solid island of trash that you can walk on or photograph from a boat. It is something more insidious and, in some ways, more difficult to confront. It is a vast, diffuse zone of elevated marine debris concentration located in the North Pacific subtropical gyre, a system of rotating ocean currents that circles between North America, Asia, and the Pacific Islands. The gyre acts as a slow, massive whirlpool, and anything that enters it, whether from rivers, coastlines, or passing ships, tends to be drawn toward the centre and trapped there. The debris is overwhelmingly plastic. In 2015, a team led by environmental engineer Roland Geyer published a landmark study estimating that since 1950, humanity has produced approximately 8.3 billion metric tons of plastic. Of that total, roughly 6.3 billion tons has become waste, and only 9% of that waste has been recycled. The rest has been incinerated, placed in landfills, or released into the environment. A significant and growing fraction of that environmental plastic ends up in the ocean. The Great Pacific Garbage Patch covers an estimated area of roughly 1.6 million square kilometres, about 3 times the size of France, though estimates vary depending on how the boundaries are defined and what concentration threshold is used. The debris ranges from large, recognisable objects like fishing nets, bottles and containers, down to microplastics, fragments smaller than 5 millimeters that result from the breakdown of larger items by sunlight, wave action, and biological processes. The microplastics are the greater concern. They are ingested by marine organisms at every level of the food chain, from zooplankton to whales. They absorb and concentrate toxic chemicals from the surrounding water. They have been found in the deepest trenches of the ocean, in Arctic sea ice, in the bodies of fish sold for human consumption, and in human blood. The garbage patch is not a problem that can be solved by simply scooping up the debris. The area is too vast, the concentration too diffuse, and the particles too small for any cleanup technology currently available to make more than a marginal dent. Several organisations, most notably the Ocean Cleanup, a Dutch non-profit, have developed systems to collect floating plastic from the surface, and these efforts have removed thousands of tons of debris. But the rate of new plastic entering the ocean continues to exceed the rate of removal. The garbage patch is growing. The deeper problem is what happens to the plastic once it enters the marine environment. Plastic does not biodegrade in the ocean. It photodegrades, meaning it breaks into smaller and smaller pieces under the influence of ultraviolet radiation. But the polymer molecules themselves persist for centuries. A plastic bottle that enters the ocean today will still be there, in some form, long after everyone alive today has died. The fragments sink, spread, and infiltrate every layer of the ocean, from the sunlit surface to the Hadal Zone. In 2019, an expedition to the bottom of the Mariana Trench found a plastic bag and candy wrappers at a depth of nearly 36,000 feet. The deepest point on Earth already has our garbage in it. The Great Pacific Garbage Patch is not a mystery in the traditional sense. We know exactly what it is, how it got there, and what it is doing to the ocean. The mystery, if there is one, is why we have not stopped it. And that is a question the ocean cannot answer for us. From the trash we put in the ocean to the wonders the ocean builds on its own, the next phenomenon is one of the most visually spectacular things the ocean produces, and almost no one has ever heard of it. Underwater waterfalls. The phrase sounds like a contradiction. A waterfall, by definition, is water falling through air. How can water fall through water? But the ocean, with its characteristic disregard for human expectations, has found a way to create something that looks, from every visual angle, exactly like a waterfall flowing downward through the water column with the same force and drama as Niagara or Victoria Falls. The most famous example occurs in the Denmark Strait, a narrow channel between Greenland and Iceland that connects the Norwegian Sea to the north with the Irminger Sea to the south. Here, cold, dense water from the Arctic flows southward and encounters warmer, less dense water moving northward. When the two bodies of water meet, the cold, heavy water plunges beneath the warm water and cascades downward along the seafloor in what oceanographers call a cataract. The Denmark Strait Cataract is the largest known underwater waterfall on Earth. It drops approximately 3,500 meters, more than 11,500 feet, making it nearly 3 times the height of Angel Falls in Venezuela, the tallest above water waterfall in the world. The volume of water flowing through the cataract is estimated at roughly 5 million cubic meters per second, a flow rate that dwarfs every river on the surface of the planet combined. The cataract is driven by thermohaline circulation, the global system of deep ocean currents powered by differences in temperature and salinity. Cold, dense water produced in the polar regions sinks to the bottom of the ocean and flows toward the equator, while warmer water at the surface flows poleward to replace it. This circulation is often described as the global ocean conveyor belt, and it is one of the primary mechanisms by which heat is distributed around the planet. The Denmark Strait Cataract is one of the most dramatic expressions of this process, a place where the sinking of cold water is concentrated into a single, powerful downflow that resembles a waterfall in every respect, except that it is entirely submerged. Another visually stunning example occurs near the island of Mauritius in the Indian Ocean, where a combination of sand and silt deposits on an underwater shelf create the illusion, when viewed from above, of a massive waterfall plunging into the deep ocean just off the coast. In this case, the waterfall is not a flow of water at all, but a visual effect created by the movement of sediment along the seafloor, swept by currents over the edge of the continental shelf and cascading downward into the abyss. Aerial photographs and satellite images of the Mauritius underwater waterfall are among the most striking ocean images ever captured, showing what appears to be a torrent of blue water being sucked into a void just offshore of a tropical paradise. The ocean, it turns out, has its own geography that mirrors the surface world in ways we are only beginning to appreciate. It has mountains and valleys, plains and canyons, rivers and, yes, waterfalls. The difference is that all of it exists in darkness, under pressure, and at scales that make their surface equivalents look modest. The Denmark Strait Cataract alone moves more water in an hour than all the rivers on Earth move in a day, and it does so in silence, in the dark, at the bottom of the Atlantic, where no human eye has ever watched it fall. The ocean does not perform for us. It does not wait for cameras or audiences. It simply does what it has always done, moving water, building and destroying, sheltering life in places we cannot reach, and creating spectacles we will never see. And yet, the more we learn about what is happening down there, the more it becomes clear that the ocean is not just a body of water, it is a a world with its own physics, its own geography, its own history, and its own rules. Rules that we are still, after centuries of sailing its surface and decades of probing its depths, only beginning to understand. The ocean is losing its ability to breathe. That statement sounds metaphorical, but it is not. Across every ocean basin on the planet, the concentration of dissolved oxygen in the water is declining. The phenomenon is called ocean deoxygenation, and its most visible consequence is the expansion of what marine scientists call dead zones, regions of the ocean where oxygen levels have fallen so low that most marine life cannot survive. Dead zones are not new. They have existed in the geologic record for hundreds of millions of years, typically associated with periods of extreme global warming that reduce the ocean's ability to absorb and circulate oxygen. But in the modern era, dead zones are expanding at an unprecedented rate. A landmark 2008 study published in the journal Science identified more than 400 dead zones in coastal waters around the world, a number that had roughly doubled every decade since the 1960s. By 2024, the count was significantly higher, though exact figures are difficult to pin down because many coastal regions, particularly in the developing world, lack the monitoring infrastructure to detect them. The causes are well understood, at least in broad terms. In coastal areas, the primary driver is nutrient pollution, particularly nitrogen and phosphorus, from agricultural runoff, sewage and industrial discharge. These nutrients fertilize the growth of algae in the water, a process called eutrophication. When the algae die, they sink to the bottom and are decomposed by bacteria, a process that consumes enormous quantities of dissolved oxygen. If the rate of oxygen consumption exceeds the rate of replenishment from the surface, the oxygen level in the bottom water drops to the point where fish, crustaceans, and other oxygen-dependent organisms either flee or die. The largest dead zone in the United States forms every summer in the Gulf of Mexico, fed by nutrient-laden water flowing down the Mississippi River from the agricultural heartland of the Midwest. At its peak, the Gulf Dead Zone can cover more than 20,000 square kilometers, an area roughly the size of New Jersey. Within this zone, the bottom water contains so little oxygen that it is classified as hypoxic, meaning it falls below the threshold necessary to sustain most marine life. Shrimp, crabs and fish that cannot escape in time are killed. The annual economic impact on Gulf Coast fisheries is estimated in the billions of dollars, but the coastal dead zones are only part of the story. In the open ocean, far from the influence of rivers and runoff, a different process is at work. As the climate warms, the surface layer of the ocean becomes warmer and lighter, increasing the density difference between the surface and the deep. This makes it harder for oxygen-rich surface water to mix downward into the deep ocean, a process called stratification. At the same time, warmer water holds less dissolved gas than cold water, meaning the surface layer itself contains less oxygen to begin with. The result is a slow, steady decline in oxygen throughout the water column, particularly in the intermediate depths where many commercially important fish species live. A 2017 study published in Nature found that the global ocean had lost approximately 2% of its dissolved oxygen since 1960, with losses concentrated in the intermediate depths between 100 and 600 meters. 2% may sound small, but in a system as finely balanced as the ocean's oxygen cycle, even modest declines can have cascading effects. Fish and other organisms that depend on specific oxygen levels are forced to compress their habitat into shallower, more oxygen-rich water, increasing competition for space and food. Species that cannot tolerate lower oxygen levels are pushed toward extinction. The ocean's dead zones are not a mystery in the traditional sense. They are a consequence, measurable and documented, of human activity on the planet's climate and ecosystems. But they are a reminder that the ocean is not an infinite reservoir. It is a system with limits, and those limits are being tested in ways that are, in some regions, already irreversible. If dead zones represent the ocean under modern stress, there is an event in the geologic past that makes our current crisis look gentle by comparison. An event so catastrophic that it transformed an entire ocean into a salt desert. Roughly 5.96 million years ago, the Mediterranean Sea dried up. The event is called the Messinian Salinity Crisis, and it is one of the most dramatic geological events in the recent history of the Earth. At the time, the Mediterranean was connected to the Atlantic Ocean through a narrow strait in what is now southern Spain and northern Morocco, a precursor to the modern Strait of Gibraltar. Tectonic activity, specifically the collision between the African and European plates, gradually narrowed and eventually closed this connection, cutting the Mediterranean off from the open ocean. Once isolated, the Mediterranean began to evaporate. The basin receives far less fresh water from rivers than it loses to evaporation, and without the inflow of Atlantic water to make up the difference, the water level began to drop. Over the course of several 100,000 years, the Mediterranean shrank and fragmented into a series of increasingly salty lakes and playas, separated by vast expanses of exposed salt flat. The evaporation deposited enormous quantities of salt on the basin floor. Layers of rock salt, gypsum, and other evaporate minerals that are in some places more than a mile thick. The total volume of salt deposited during the Messinian Salinity Crisis accounts for roughly 6% of all the dissolved salt in the world's oceans, extracted from the Atlantic and locked away beneath the Mediterranean in a geological blink of an eye. The ecological consequences were catastrophic. The marine life of the Mediterranean, which had evolved over millions of years in a warm, connected sea, was almost entirely wiped out. Species that could not migrate out through the closing strait before it sealed were trapped in water of ever-increasing salinity, until nothing could survive. The basin, once a thriving marine ecosystem, became one of the most inhospitable environments on the planet's surface, a salt desert sitting several kilometers below the level of the surrounding terrain. The crisis ended as abruptly as it began. Approximately 5.33 million years ago, the barrier separating the Atlantic from the Mediterranean was breached. The event, known as the Zanclean Flood, is believed to have been one of the most spectacular geological catastrophes in Earth's history. Atlantic water poured through the breach in a torrent, estimated at more than 1,000 times the flow of the Amazon River, cascading down into the empty basin, in a waterfall that may have been kilometers wide and hundreds of meters tall. The refilling of the Mediterranean is estimated to have taken between several months and a few thousand years, depending on the model used, transforming a salt desert back into a sea in a geological instant. The evidence for the Messinian Salinity Crisis is written in the rocks beneath the modern Mediterranean. Deep-sea drilling projects in the 1970s recovered cores of rock salt from beneath the seafloor, confirming that the basin had indeed been dry or nearly dry at some point in the geologic past. Seismic surveys have mapped the thick evaporate layers beneath the Mediterranean floor and erosional features on the surrounding coastlines, including deep river canyons that were carved when the base level of the Mediterranean dropped by hundreds of meters, provide additional evidence. The Messinian Salinity Crisis is a reminder that the ocean, which we think of as permanent and unchanging, is neither. It is a feature of a planet in constant motion, shaped by tectonic forces that can open and close gateways between seas, raise and lower coastlines, and transform entire ocean basins from thriving ecosystems to lifeless salt flats and back again. The Mediterranean Sea, which today supports some of the densest human populations and longest cultural histories on Earth, was, less than 6 million years ago, a barren, salt-encrusted wasteland. The ocean has a longer memory than we do, and its history includes chapters that make our current challenges look modest. But even as we struggle to understand the ocean's past and protect its present, a new frontier is opening that could transform the deep sea in ways that are difficult to predict and potentially impossible to reverse. The frontier of deep-sea mining. The floor of the deep ocean is scattered with mineral deposits of extraordinary value. The most sought after are polymetallic nodules, potato-sized lumps of metal that form over millions of years on the abyssal plains of the Pacific, Atlantic, and Indian Oceans. The nodules are rich in manganese, nickel, cobalt, and copper, metals that are critical to the production of batteries, electronics, and renewable energy technology. A single nodule can contain higher concentrations of these metals than most terrestrial ore deposits, and the total reserves on the ocean floor are estimated to be worth trillions of dollars. The technology to mine these nodules is now available. Several companies backed by national governments and private investors have developed systems capable of vacuuming the nodules from the seafloor at depths of 4,000 to 6,000 meters. The collected material would be lifted to the surface through long risers, separated from the sediment, and transported to processing facilities on land. Pilot projects have been conducted. Feasibility studies have been completed. Applications for commercial mining permits have been filed with the International Seabed Authority, the United Nations body responsible for regulating activities on the ocean floor in international waters. The environmental concerns are profound. The abyssal plains where polymetallic nodules are found are among the most stable environments on Earth. The organisms that live there have adapted to conditions of near total darkness, crushing pressure and extremely low rates of energy input. They grow slowly, reproduce infrequently, and are likely to recover from disturbance on timescales of centuries to millennia, if they recover at all. Mining operations would physically remove the nodules from the seafloor, destroying the habitat they provide for organisms that attach to their surfaces. The vacuum systems would disturb the upper layer of sediment, generating plumes of fine particles that could spread across thousands of square kilometers, smothering filter feeders and disrupting ecosystems far from the mining site itself. The 2024 Chile Deep Sea Expedition, which discovered over 100 new species in a single stretch of water, added urgency to the debate by demonstrating that the areas proposed for mining may harbour species that have not yet been identified, let alone studied. Critics argue that allowing commercial mining to proceed before the ecosystems of the deep sea floor have been adequately surveyed is reckless, equivalent to clearing an uncharted forest before determining what lives in it. Proponents of deep-sea mining counter that the metals on the ocean floor are essential to the global transition away from fossil fuels. Electric vehicles, wind turbines, and solar panels all require significant quantities of cobalt, nickel, and other metals that are currently sourced from terrestrial mines with their own severe environmental and humanitarian costs. Mining the ocean floor, they argue, could provide these metals with a smaller overall footprint than expanding land-based mining. The debate is ongoing and contentious. As of early 2025, no commercial deep-sea mining operation had received final approval from the International Seabed Authority, but the pressure to begin was mounting. The decisions made in the next few years will determine whether the deep ocean, the last largely untouched ecosystem on the planet, is open to industrial extraction. And unlike the forests and rivers on land, the deep ocean has no constituency, no voters and no voice. Whatever is decided will be decided by people who have never been there and may never go. The ocean's mysteries are not all ancient. Some of them are being written right now. The ghost ship phenomenon did not end in the age of sail. The ocean is still producing them. On April 15th, 2007, the Australian Maritime Authorities received a report of an unmanned catamaran drifting in the open waters of the Coral Sea, roughly 88 nautical miles off the coast of Queensland. The vessel was a 40-foot catamaran named Cas2, and it had departed Airlie Beach in the Whitsunday Islands 3 days earlier, crewed by 3 experienced sailors, Derek Batten, Peter Tunstead, and James Tunstead, who were brothers. The men were headed north along the Great Barrier Reef, a voyage they had made before. The weather was fair. The sea was calm. When the Cas2 was spotted by a search helicopter and subsequently boarded by emergency crews, the scene was disturbingly familiar. The vessel was in good condition, The engine was running. The sails were set but damaged, as though the boat had been sailing without anyone to trim them. A laptop computer was open on the table, still powered on. The GPS navigation system was active. Food was laid out. The men's personal effects were aboard. Life jackets were stowed in their usual location, unused. The 3 men were gone. A subsequent investigation by the Queensland Coroner's Office lasted several months and included forensic analysis of the vessel, reconstruction of weather and sea conditions along the route, and expert testimony from experienced sailors and maritime safety officials. A video camera found aboard the CAS-2 had recorded footage from the early hours of the voyage, showing the 3 men in good spirits, handling the boat competently. But the camera had been switched off or run out of battery before whatever happened took place. The coroner's report, issued in September 2008, concluded that the most likely scenario was a tragic accident involving a combination of factors. One of the men may have been pulled overboard by a fishing line or by a sudden wave while retrieving something from the water. One or both of the others may have gone in to help and been unable to return to the boat. The catamaran, with its engine still running and its sails catching the wind, would have continued moving, pulling away from the men in the water faster than they could swim. The flat underside of a catamaran is notoriously difficult to climb back onto from the water, especially without a ladder deployed, and the investigators found that the rear boarding ladder on the CAS-2 was not extended. No bodies were ever recovered. The Coral Sea, with its strong currents and abundant sharks, is not a forgiving place for anyone stranded in the water. The coroner found no evidence of foul play, no indication that the men had been in conflict with each other or with anyone else, and no sign that the boat had been boarded by pirates or suffered any kind of mechanical catastrophe. The most likely explanation was the simplest and the most tragic. A moment of bad luck, a lapse in safety protocol, and the indifference of a moving vessel to the men who had been sailing it seconds before. The CAS-2 became known in the Australian media as the Ghost Yacht, and the parallels to the Mary Celeste were noted immediately and widely. The same ingredients were present: a sound vessel, missing crew, no explanation that fully satisfies, and the ocean, as always, offering no comment. What connects the CAS-2 to every other ghost ship in history is not the specifics of what happened, but the feeling the stories produce. The sense that the boundary between safety and a catastrophe at sea is thinner than we think. That a ship, no matter how well maintained, how carefully crewed, how precisely navigated, is always just one unexpected moment away from becoming an empty vessel, drifting without purpose. The ocean does not need drama to kill. It does not need storms or rogue waves or sea monsters. Sometimes all it needs is a fish on a line, a man leaning over the rail in a boat that keeps going. The sea is patient. It waits for the small mistakes, and it never gives anyone back. Where the ocean gathers its dead and its debris tells us as much about how the sea works as any laboratory experiment. And some of the most revealing locations are the convergence zones, the places where currents meet and everything the ocean has been carrying is brought together in a single, concentrated line. Ocean convergence zones form wherever 2 currents flowing in different directions meet head-on or at an angle. The water, unable to continue in its original direction, is forced downward, creating a narrow band of sinking water that draws floating material from both sides into a visible line on the surface. From the air, convergence zones look like seams in the fabric of the ocean, long irregular streaks of foam, seaweed, debris and marine life stretching for miles across otherwise featureless water. These zones are ecological hotspots. The sinking water along the convergence line draws nutrients from both sides, creating a concentrated band of productivity that attracts plankton, small fish, and in turn the larger predators that feed on them. Tuna, mahi-mahi, marlin and sharks all congregate along convergence lines, making them prize fishing grounds. Seabirds wheel overhead in enormous flocks, diving for fish that have been corralled into the narrow band of enriched water. Sea turtles, whales and dolphins pass through, feeding on the abundance. But convergence zones also concentrate everything else the ocean is carrying. Plastic debris, fishing gear, oil slicks, and chemical runoff all accumulate along the same lines that attract marine life. Some of the most polluted stretches of ocean on the planet are found along convergence zones, where the same currents that bring nutrients also bring trash. The Great Pacific Garbage Patch, which we discussed earlier, is essentially a very large, very slow, convergence zone, a region where the circular currents of the North Pacific subtropical gyre bring everything they have collected to a single rotating accumulation area in the centre. The tragic irony is that the places in the ocean where life is most abundant are often the same places where pollution is most concentrated. Marine animals that congregate along convergence lines to feed are exposed to the highest concentrations of microplastics, chemical pollutants, and discarded fishing gear in the ocean. Sea turtles, which are attracted to convergence zones because the same currents that accumulate debris also accumulate the jellyfish and sargassum weed they eat, are among the species most heavily impacted by plastic ingestion. The ocean does not separate its gifts from its poisons. They travel the same currents and arrive at the same destinations. Understanding convergence zones is critical to understanding how the ocean distributes everything from heat and nutrients to garbage and toxic chemicals. They are the ocean's circulatory system made visible, the places where the invisible machinery of currents and winds produces tangible, concentrated effects on the surface. And they are a reminder that in the ocean, nothing stays where you put it. Everything moves, everything circulates, and everything eventually ends up somewhere it was not intended to go. From the currents that carry the ocean's detritus to the deep where its most famous wrecks rest, there is one ship whose fate is not a mystery in the traditional sense, but whose ongoing story in the deep sea is as extraordinary as any unsolved disappearance: the Titanic. On April 15th, 1912, the RMS Titanic sank in the North Atlantic after striking an iceberg during her maiden voyage from Southampton to New York City. The loss of more than 1,500 lives made it one of the deadliest maritime disasters in history, and one of the most thoroughly documented events of the 20th century. The story of the sinking has been told countless times, in books, films, and exhibitions, but the story of what happened to the Titanic after she reached the bottom is less well known, and it is in its own way equally remarkable. The wreck of the Titanic lies on the floor of the North Atlantic at a depth of approximately 12,500 feet, roughly 370 miles south-southeast of the coast of Newfoundland. She was discovered on September 1st, 1985, by a joint American-French expedition led by Robert Ballard of the Woods Hole Oceanographic Institution and Jean-Louis Michel of the French National Oceanographic Agency, IFREMER. Ballard's team located the wreck using a towed deep-sea camera system called Argo, which transmitted live video of the ocean floor to monitors on the surface ship. When the first images of the Titanic's hull appeared on the screens, Ballard later recalled, the room went completely silent. The ship was found broken in two. The bow section, largely intact, sat upright on the seabed, its prow buried in the mud. The stern section, about 600 meters away, was in far worse condition, crumpled and twisted by the force of its impact with the bottom after plunging nearly 2.5 miles through the water column. Between the two main sections, a vast debris field stretched across the seafloor, containing everything from personal effects and dinnerware to pieces of the ship's hull and machinery. But the most striking discovery was biological. The Titanic was being consumed. The steel hull was covered in long reddish-brown stalactites of rust, some of them several feet long, produced by a previously unknown species of iron-oxidizing bacteria. These organisms, later named Holomonas titanicae in honor of the ship, were literally eating the Titanic, converting the iron in her hull into rust at a rate that researchers initially estimated would reduce the wreck to an unrecognizable pile of debris within decades. The bacteria work by oxidizing the iron in the steel, converting it to iron hydroxide and other compounds that form the distinctive rusticles the icicle-shaped formations that hang from every surface of the wreck. Each rusticle is a complex community of microorganisms, not just the iron-eating bacteria, but also fungi, archaea, and other organisms that have colonized the formations and created a tiny ecosystem. The rusticles grow slowly but steadily, and as they do, they dissolve the structural steel beneath them. When Ballard first visited the wreck in 1985, the bow section was still recognizable as a ship. The deck rails were visible. The bridge was identifiable. Portholes still glinted in the lights of the submersible. By the 2000s, the deterioration was noticeable. The mast had collapsed, sections of the deck were buckling, the officers' quarters were caving in. In 2019, a new expedition using advanced deep-sea diving technology found that the rate of deterioration had accelerated. The captain's bathtub, a landmark feature of the wreck that had been visible and intact for decades, was gone, consumed by the bacteria and the relentless chemistry of the deep sea. Current estimates suggest that the Titanic may be entirely gone, reduced to an indistinguishable pile of rust and sediment within a few more decades. Some researchers put the timeline at as little as 30 to 40 years from now. The ship that was built to be unsinkable is proving to also be unpreservable. The deep ocean, with its cold temperatures, high pressures, and patient microorganisms, is slowly reclaiming her. In 2023, the tragedy of the Titanic's deep-sea location was underscored by the loss of the Titan submersible, a privately operated vessel that imploded during a descent to the wreck site, killing all 5 people aboard. The disaster highlighted both the enduring fascination of the Titanic and the extreme dangers of deep-sea exploration. The Titanic sits at a depth where the water pressure is approximately 6,000 pounds per square inch, an environment so unforgiving that even the slightest engineering flaw can be fatal. The Titanic is not a mystery. We know where she is. We know how she sank. We know who was aboard. But her slow dissolution on the ocean floor is a vivid illustration of one of the ocean's most fundamental qualities. Everything that enters the water eventually belongs to the water. Even a 46,000-ton ocean liner, even one made of steel, is temporary. The ocean has all the time in the world and it uses every minute of it. The deep is patient, and it does not distinguish between a drifting plastic bottle and the most famous shipwreck in history. Both will, in time, be reclaimed. Both will eventually disappear. There is a change happening in the ocean right now that is invisible to the naked eye, silent, and almost completely unfelt by anyone walking along a beach or sailing across open water. But it is one of the most consequential transformations in the chemistry of the planet's oceans in at least 300 million years. The ocean is becoming more acidic. Since the beginning of the Industrial Revolution, the burning of fossil fuels has released enormous quantities of carbon dioxide into the atmosphere. The ocean, which has always absorbed carbon dioxide from the air as part of the global carbon cycle, has taken up roughly 30% of the excess CO2 produced by human activity. In absolute terms, that is about 525 billion tons of carbon dioxide absorbed since the mid-18th century. For a long time, this absorption was viewed as a good thing, a natural buffer that was helping to slow the build-up of greenhouse gases in the atmosphere and moderate climate change. But the chemistry of what happens to carbon dioxide when it dissolves in seawater is not benign. When CO2 enters the ocean, it reacts with the water to form carbonic acid. This acid then dissociates, releasing hydrogen ions and lowering the pH of the seawater. Since pre-industrial times, the average pH of the ocean surface has dropped from approximately 8.2 to about 8.1. That sounds trivial. It is not. The pH scale is logarithmic, meaning each whole number change represents a tenfold change in acidity. A drop of 0.1 pH units represents a roughly 30% increase in the concentration of hydrogen ions in the water. The ocean is 30% more acidic than it was before the Industrial Revolution, and the rate of change is accelerating. The consequences for marine life are serious and well documented. Many marine organisms, including corals, mollusks, sea urchins, and certain species of plankton, build their shells and skeletons from calcium carbonate. As the ocean becomes more acidic, the concentration of carbonate ions in the water decreases, making it harder for these organisms to form and maintain their structures. In laboratory experiments, increased acidity has been shown to dissolve the shells of pteropods, tiny planktonic snails that form a critical part of the food web in the Southern Ocean. Coral reefs, which are already under severe stress from rising temperatures, face an additional threat from acidification that could push many reef systems past the point of recovery. The ecological impacts cascade upward through the food chain. Pteropods are eaten by fish. Fish are eaten by seabirds, seals, and whales. Coral reefs support an estimated 25% of all marine species. The degradation of any of these components has the potential to destabilize entire ecosystems. And unlike many other environmental stresses, ocean acidification cannot be reversed quickly. Even if carbon dioxide emissions were eliminated entirely today, the ocean would take thousands of years to return to its pre-industrial chemistry. Ocean acidification is sometimes called climate change's equally evil twin, and the description is apt. While the warming of the atmosphere and the ocean surface receives most of the public attention, the chemical transformation happening beneath the surface is potentially even more destructive and even less reversible. It is a slow-moving crisis in a medium that most people never see and rarely think about. And it is, like so many of the ocean's processes, operating on a timescale that makes it easy to ignore until the consequences become impossible to miss. The ocean absorbs our excess. It always has. But there is a price for that absorption, and we are only now beginning to understand what it is. If the chemistry of the ocean is changing in ways that threaten its smallest and most vulnerable inhabitants, the deep ocean continues to harbour creatures at the opposite end of the scale. Animals so large and so elusive that even in the 21st century, with all our cameras and submersibles and satellites, they have been seen alive in the wild only a handful of times. The colossal squid, Messonychoteuthis hamiltoni, is believed to be the heaviest invertebrate on Earth. It is distinct from the giant squid, Architeuthis dux, which is more famous but probably not as massive. While the giant squid is longer, with tentacles that can extend to over 40 feet, the colossal squid has a thicker, heavier body and shorter, more muscular arms equipped with a feature unique among known cephalopods: rotating hooks. The suckers on the colossal squid's arms and tentacles are lined with sharp, swiveling hooks that can grip and shred prey with a ferocity that no other squid can match. Almost everything we know about the colossal squid comes from specimens recovered from the stomachs of sperm whales or from rare captures by deep-water fishing operations. The species was first described scientifically in 1925, based on 2 arm fragments found in the stomach of a sperm whale. In the century since, complete or near-complete specimens have been recovered fewer than a dozen times. The largest intact specimen, captured by a New Zealand fishing vessel in the Ross Sea off Antarctica in 2007, measured approximately 33 feet in length and weighed over 1,000 pounds. But based on the size of beaks and other fragments found in sperm whale stomachs, researchers believe that fully grown colossal squid may be significantly larger than any specimen yet recovered. The eyes of the colossal squid are among the largest in the animal kingdom, measuring up to 11 inches in diameter, roughly the size of a dinner plate. They are adapted for detecting the faintest traces of light in the near-total darkness of the deep Southern Ocean, where the species is believed to spend most of its life at depths between 1,000 and 2,000 meters. The squid is thought to be an ambush predator, hanging motionless in the dark and waiting for prey, primarily fish and other squid, to pass within striking range. Despite its size and its formidable armament, the colossal squid is poorly understood. No one has ever observed one hunting in the wild. No one knows how they reproduce, how long they live, or what their population numbers are. The deep Southern Ocean, where they are believed to reside, is one of the most remote and least explored bodies of water on the planet, and the extreme depths at which the squid lives make direct observation extraordinarily difficult. What we do know comes mostly from the animals that eat them. Sperm whales are the primary predator of colossal squid, and the scars left by the squid's rotating hooks on the skin of sperm whales are among the most dramatic evidence of the battles that take place in the deep ocean, far below the surface. Some sperm whales bear circular scars the size of dinner plates, suggesting encounters with squid of enormous proportions. The frequency of colossal squid beaks in sperm whale stomachs suggests that the species is not rare, merely invisible to us, living its entire life in a realm that human technology can barely reach. The colossal squid is a reminder that the deep ocean still harbours megafauna that we have barely glimpsed. For every species we have named and described, there may be others that have never been captured, never been photographed, and never risen close enough to the surface for anyone to know they exist. The deep ocean is vast, dark, and almost entirely unsurveyed. What swims through it is, in large part, a matter of educated guessing. And the colossal squid, with its hooks and its dinner plate eyes and its body that may exceed any specimen we have yet recovered, is proof that the guesses are probably conservative. And while the colossal squid patrols the deep southern ocean, the sea floor beneath it harbours yet another phenomenon that defies intuitive understanding. Because just as the ocean contains underwater lakes in its brine pools and underwater waterfalls in its cataracts, it also contains something that can only be described as underwater rivers. In several locations around the world, dense flows of sediment-laden water have been observed moving along the seafloor in channels that look, from every perspective, like rivers. They have banks, they have meanders, they erode the sediment on either side and deposit material at their mouths and deltas, just like rivers on land. But instead of flowing through a landscape of soil and rock, they flow through the ocean, carving their courses across the mud and silt of the continental shelves and abyssal plains. The most well-documented underwater river flows along the seafloor of the Black Sea, where a current of highly saline water from the Mediterranean enters through the Bosphorus, and being denser than the less saline Black Sea water, sinks to the bottom and flows along a defined channel across the seabed. The channel is complete with banks, floodplains, and even what appear to be rapids, where the terrain changes gradient. Researchers who mapped the formation estimated that if it were on land, it would be the 6th largest river in the world by flow volume. Similar phenomena have been observed in other locations, including the deep sea floor off the coasts of Brazil, Australia and West Africa. In each case, the underwater rivers are formed by density differences, where water of one salinity or temperature encounters water of a different density, and instead of mixing, flows along the bottom in a distinct channelized current. The channels can persist for hundreds of miles, carving into the sea floor over thousands of years and creating submarine canyons that rival the scale of their terrestrial counterparts. The Grand Bahama Canyon, for example, is one of the deepest and most dramatic submarine canyons in the Atlantic, carved by underwater density currents flowing from the shallow Bahama banks into the deep ocean. The canyon plunges to depths of over 14,000 feet and extends for more than 100 miles. It was carved not by a river of fresh water, but by a river of dense sediment-laden seawater, moving slowly but relentlessly across the seafloor, eroding and depositing with the same patient power that terrestrial rivers use to carve valleys through mountains. The ocean floor is not a passive, static surface. It is a dynamic landscape shaped by forces that are, in many cases, directly analogous to the forces that shape the land. There are rivers down there. There are waterfalls. There are lakes. There are mountains, volcanoes, and canyons deeper than any on the surface. The only difference is that all of it exists in darkness, under pressure, and largely beyond the reach of human observation. We know it is there because instruments have detected it. But seeing it, understanding it, and mapping it in the kind of detail we take for granted on land remains one of the great unfinished tasks of earth science. The ocean is not featureless. It is a world unto itself, With a geography as complex and varied as the continents above, we have simply not yet learned to see it. If you were asked to name the least explored part of the ocean, you would probably say the bottom, the abyssal plains, the trenches, the Hadal Zone. Those are the places that appear in documentaries and headlines, the deepest, darkest, most dramatic frontiers of exploration. But you would be wrong. The least explored part of the ocean is not the bottom. It is the middle. The pelagic zone, the vast open expanse of water that sits between the sunlit surface and the ocean floor, is the largest habitable space on the planet. It encompasses roughly 1.3 billion cubic kilometers of water, stretching from the edge of the continental shelves to the centers of the ocean basins, and from just below the sunlit surface layer to just above the seafloor. It is by volume the single largest ecosystem on Earth, and it is the one we know the least about. A 2010 analysis conducted by a collaboration between the University of Sheffield, the Ocean Biogeographic Information System at Rutgers University, and the Consortium for Ocean Leadership attempted to quantify the geographic gaps in our knowledge of marine life. The team geotagged the known locations of identified aquatic species and then mapped the gaps, the places where no species had been documented. The result was stark. The open pelagic ocean, the water column itself, was overwhelmingly the least surveyed environment in the sea. We know more about the organisms that live on the ocean floor, more about the species that inhabit coral reefs and coastal shallows, and more about the creatures in the deepest trenches than we know about the life drifting through the vast, dim middle of the ocean. The reason is partly practical. The pelagic zone is featureless. From a navigation and research standpoint, there are no landmarks, no structures, no surfaces to attach instruments to. Organisms in the pelagic zone are constantly moving, carried by currents and undertaking vertical migrations that can span hundreds of meters each day. Studying them requires either following them, which is logistically challenging across the enormous distances involved, or waiting for them to come to you, which is unreliable. The creatures of the open ocean are, by their nature, dispersed and elusive. They do not congregate around convenient observation points like hydrothermal vents or coral reefs. They live in the water itself, and the water is vast. What we do know about the pelagic zone is tantalizing. It is home to the largest animal migration on Earth, a daily event so enormous that it can be detected by sonar. Every night, trillions of organisms, from tiny copepods and krill to jellyfish, squid, and lanternfish, rise from the deep mesopelagic zone between 200 and 1,000 meters to the surface waters to feed under cover of darkness. At dawn, they descend again, retreating to the safety of the deep where predators cannot see them. This deal vertical migration, as scientists call it, is the largest synchronized movement of biomass on the planet. It happens every day, in every ocean, and it has been happening for hundreds of millions of years. The migration plays a critical role in the global carbon cycle. The organisms that rise to feed at the surface consume phytoplankton, tiny photosynthetic organisms that have absorbed carbon dioxide from the atmosphere. When the migrants descend back to the deep, they carry that carbon with them in the form of their bodies and their waste, effectively transporting carbon from the atmosphere to the deep ocean in a process called the biological pump. Disruptions to the vertical migration, whether from overfishing, pollution, or climate change, could impair the ocean's ability to sequester carbon and accelerate the buildup of greenhouse gases in the atmosphere. Despite its importance, the pelagic zone remains one of the most data-poor environments on the planet. The organisms that live there are fragile, often transparent or gelatinous, and many of them disintegrate when brought to the surface by nets or collection devices. New species are discovered regularly, but the rate of discovery is limited by the difficulty of observing them in their natural habitat. The development of advanced autonomous underwater vehicles, equipped with cameras, sensors and sampling systems, is beginning to open this frontier. But the pelagic zone is so enormous and so uniform that comprehensive surveys may take generations to complete. The middle of the ocean is not empty, it is teeming with life, but that life exists in a form and at a scale that our current tools are only beginning to capture, and the medium through which all of this life moves, the water itself, has a property so remarkable that it transformed military strategy, enabled the tracking of whales across entire ocean basins, and ultimately solved the mystery of the bloop. It is the ocean's ability to carry sound. Sound travels through water roughly 4.5 times faster than through air, and at certain depths it travels with almost no loss of energy over distances that would be impossible in any other medium. This is because of a layer in the ocean called the SOFAR channel, an acronym for sound fixing and ranging. The SOFAR channel exists at a depth of roughly 800 to 1,200 meters in most of the world's oceans, though the exact depth varies with temperature and salinity. At this depth, the combination of decreasing temperature and increasing pressure creates a minimum in the speed of sound. Sound waves that enter this layer are refracted back toward the center of the channel whenever they try to escape, trapped in a natural waveguide that can carry acoustic signals for thousands of miles. The US Navy discovered the SOFAR channel during World War II and immediately recognized its military potential. During the Cold War, the Navy built the SOSUS network, an array of hydrophones positioned in the SOFAR channel across the Atlantic and Pacific, to track the movements of Soviet submarines by listening for the distinctive acoustic signatures of their engines and propellers. The system was extraordinarily effective. A submarine running its engines in the Norwegian Sea could be detected by hydrophones in Bermuda. When the Cold War ended, the SOSUS network and its successor arrays were repurposed for scientific research, and they opened an entirely new window into the ocean's acoustic world. Researchers discovered that the ocean is far from silent. It is a cacophony of sound, produced by earthquakes, volcanic eruptions, calving icebergs, wind waves, marine mammals, shrimp, fish, and countless other sources. Blue whales, which produce some of the loudest and lowest frequency sounds of any animal, were found to be communicating across entire ocean basins, their calls travelling thousands of miles through the SOFAR channel. Fin whales, humpback whales, and sperm whales were all tracked by their vocalizations, revealing migration patterns and population structures that had been invisible to surface-based observation. The same hydrophone networks that tracked submarines and whales also captured the mysterious sounds that became the subject of worldwide fascination. The bloop, Julia slowdown, upsweep, and the train were all detected by NOAA's acoustic monitoring program, descendants of the military listening arrays. Most were eventually attributed to ice activity or geological processes, but the fact that they were detected at all across distances of thousands of miles is a testament to the extraordinary acoustic properties of the ocean. Human activity is increasingly adding to the ocean's noise. Shipping traffic, sonar, seismic air guns used in oil and gas exploration, and underwater construction all produce sound that propagates through the water with the same efficiency as natural sources. The cumulative effect of this anthropogenic noise is a growing concern for marine biologists, particularly for species that depend on sound for communication, navigation, and hunting. Whales, dolphins, and other marine mammals are especially vulnerable. Studies have shown that increased ocean noise can disrupt feeding behavior, interfere with mating calls, cause physical injury at close range, and drive animals away from critical habitats. The ocean's ability to carry sound is one of its most remarkable and most exploited properties. It has given us the ability to listen to the deep from the comfort of a shore-based laboratory, to track whales across hemispheres, and to detect geological events occurring on the opposite side of the planet. But it has also created a new kind of pollution, invisible and pervasive, that is transforming the acoustic environment in which marine life has evolved over millions of years. The ocean that once belonged to the whales is getting louder, and they cannot close their ears. From the sound channels of the deep to the surface of the tropical seas, the ocean has one more biological wonder to show us before we reach the end of this journey, a creature so small you could hold it on your fingertip, yet possessed of an ability that no other animal on Earth is known to have, the ability to reverse aging. Turritopsis dohanii is a species of jellyfish, barely 5 millimeters across when fully grown, found in temperate and tropical waters around the world. In most respects it is unremarkable. It feeds on plankton. It drifts with currents. It is transparent and nearly invisible in the water. But Turritopsis dohanii has earned a nickname that sets it apart from every other organism on the planet. It is called the immortal jellyfish. The name is not entirely accurate, but it is not entirely wrong either. Most jellyfish have a simple life cycle. They begin as larvae, settle on a surface and develop into polyps, and then transform into the bell-shaped medusa that most people recognize as a jellyfish. The medusa stage is the adult form. It reproduces sexually, releases eggs or sperm into the water, and eventually dies. It is a one-way journey. Larva to polyp, to medusa, to death. Turritopsis dohanii can reverse the process. When the adult medusa is stressed, injured, or simply old, it can transform itself back into its juvenile polyp stage, essentially rewinding its biological clock to an earlier state of development. The polyp can then grow and mature again, producing a new medusa that is, genetically, the same individual. The cycle can, in theory, repeat indefinitely. Turritopsis dohanii does not age in the way that every other multicellular animal ages. It does not progress inevitably from youth to maturity to decline. It loops. The mechanism behind this process is called transdifferentiation, a phenomenon in which one type of specialized cell transforms into a different type of specialized cell. In the case of Turritopsis dohanii, the mature cells of the medusa revert to their earlier, less specialized forms, and then re-specialize as polyp cells. It is as though an adult human could, under stress, transform back into an infant and start growing again. The discovery of this ability, first documented in the mid-1990s by researchers in Italy, generated enormous scientific interest. If the process could be understood at the molecular level, it might provide insights into cellular aging, regeneration, and even cancer, which involves a different kind of cellular transformation. In 2022, a team of Spanish scientists published a detailed analysis of the Turritopsis dohanii genome, identifying genes associated with DNA repair, telomere maintenance, and stem cell regulation that appear to be uniquely amplified or modified in this species compared to related jellyfish. But the immortal jellyfish is not truly immortal. It can still be eaten by predators, killed by disease, or destroyed by environmental changes. What it has escaped is the biological inevitability of aging. In the wild, most Turritopsis dohanii individuals probably die of predation or environmental stress, long before they have the chance to cycle back to their polyp stage. But in laboratory conditions, individuals have been observed undergoing the transformation multiple times, suggesting that the potential for indefinite cycling is real. The immortal jellyfish is not going to grant us eternal life, but it is a reminder that the ocean's biological toolkit is far more diverse and far more inventive than the examples we see on land. The strategies for survival that evolution has produced in the marine environment, from the 500-year lifespan of the Greenland shark to the transdifferentiation of a 5mm jellyfish, encompass possibilities that terrestrial biology has never explored. The ocean is not just a habitat, it is a laboratory, and the experiments it is running have been going on for billions of years, producing results that we are only now beginning to catalogue. The water holds more answers than we have questions, and every time we look closer, we find something we did not expect. We have travelled tonight from the surface to the deepest point on the planet. We have followed ghost ships across the Atlantic and listened to sounds that crossed entire oceans. We have watched structures on the seafloor confound geologists, and we have met creatures that have outlived every civilization that has ever existed on land. But before we surface for the last time, there is one more place to visit: the the largest and least known landscape on Earth, the abyssal plain. If you could drain the ocean, the single most dominant feature of the planet's surface would not be mountains, or deserts, or forests, or ice sheets. It would be the abyssal plains. These vast flat expanses of sediment-covered seafloor extend across every ocean basin at depth between 3,000 and 6,000 meters. They cover more than 50% of the Earth's total surface area, making them, collectively, the single largest habitat on the planet, and they are, overwhelmingly, the least explored. The abyssal plains are formed by the slow, continuous rain of fine particles from the water above. Dead plankton, silt, clay, volcanic ash, and cosmic dust that drifts downward through thousands of meters of water and settles on the ocean floor. Over millions of years, this particle rain has buried the rough, volcanic terrain of the mid-ocean ridges and seamounts under a thick blanket of sediment, creating landscapes of almost perfect flatness. In some areas, the seafloor is level to within a few meters over distances of hundreds of kilometers. It is the flattest terrain on the surface of the Earth, smoother than any prairie, any salt flat, any stretch of ice. Life on the abyssal plain is sparse but persistent. The organisms that live there, primarily worms, sea cucumbers, brittle stars, and tiny crustaceans, subsist on the thin rain of organic particles from the surface, supplemented occasionally by larger falls of dead whales or other marine animals. A whale carcass that reaches the abyssal plain, called a whale fall, can sustain an entire community of scavengers and decomposers for decades. The initial scavengers, sleeper sharks, hagfish, and giant isopods, consume the soft tissue in a matter of months. Smaller organisms colonize the bones, feeding on the lipids stored within. Specialized bacteria break down the bone itself, and a unique community of tube worms and other organisms can persist at the site for 50 years or more, long after any visible trace of the whale has disappeared. The abyssal plain is also the repository for everything the ocean carries: microplastics, pollutants, sediment from rivers that emptied into the sea millennia ago, and the remains of every organism that ever lived in the water above. All of it eventually reaches the bottom and joins the slow accumulation of the deep. The sediment record on the abyssal plain is, in a very real sense, the autobiography of the planet, a layer-by-layer account of everything that has happened on the surface of the Earth, written in particles too small to see and stored in a library too deep to reach. Cores drilled from the abyssal sediment have revealed the history of ancient climates, mass extinctions, asteroid impacts, and volcanic eruptions. The boundary between the Cretaceous and Paleogene periods, the moment 66 million years ago, when an asteroid struck the Earth and ended the age of the dinosaurs, can be found in abyssal sediment cores as a thin layer of iridium-enriched clay, deposited by the global dust cloud that followed the impact. The rise and fall of ice ages, the opening and closing of ocean gateways, and the evolution and extinction of countless marine species are all recorded in the mud at the bottom of the sea. The abyssal plain is where the ocean keeps its records, and most of those records have never been read. It is also the target of the deep-sea mining industry, as we discussed earlier. The polymetallic nodules that mining companies seek are found predominantly on the abyssal plains, scattered across the sediment like dark, irregular stones. These nodules grow at a rate of roughly 1 centimeter per million years, meaning that each one is a physical record of millions of years of chemical and geological processes. Removing them is not like harvesting a crop. It is like tearing pages from a book that took millions of years to write and can never be rewritten. The abyssal plain is the most common landscape on Earth and the one we understand the least. It is a place of astonishing monotony and astonishing patience, where time moves at a geological pace and every change is measured in millimeters per millennium. It is the resting place of everything the ocean has ever carried and the birthplace of everything the ocean will ever build. And it is, for now, almost entirely beyond our reach. We began this journey at the surface, with a ship drifting without her crew in the Atlantic. We descended through layers of mystery and wonder, through sounds and structures, creatures and currents, until we reached the deepest, flattest, most silent place on the planet, the abyssal plane, the bottom of everything. And what we have found at every depth and in every ocean is the same fundamental truth. The ocean is not an empty space between the continents. It is a world with its own history that stretches back billions of years, its own geography that dwarfs anything on land, its own biology that operates by rules we are only beginning to learn, and its own secrets that it guards with a patience and a completeness that no human institution can match. We have been exploring the ocean for thousands of years. We have sailed its surface, mapped its currents, charted its coastlines, and sent cameras and submersibles into its deepest trenches. And after all of that, we have surveyed barely a quarter of its floor. We have identified perhaps 10% of its species. We have sampled a tiny fraction of its chemistry. The ocean is not running out of mysteries. It is generating them faster than we can solve them. The Mary Celeste has been empty for 150 years, and no one knows why. The USS Cyclops lies somewhere on the Atlantic floor with 306 souls, and no search has found her. The Yonaguni Monument sits off the coast of Japan, its origin unresolved. The colossal squid patrols the deep southern ocean, and no one has ever watched it hunt. The Greenland shark drifts through Arctic waters that it has known for half a millennium, blind and patient, carrying memories locked in the crystals of its ancient eyes. These are not stories from the past, they are ongoing. The bloop was solved, but new unidentified sounds are recorded every year. The garbage patch is growing, the dead zones are expanding, the ice is melting, and as it does, it is releasing sounds into the ocean that no microphone has recorded before. New species are being discovered, and new species are going extinct, sometimes before we even know they existed. The ocean is changing faster now than at any point in the last several million years, and we are watching it happen with instruments that can see barely a fraction of what is going on. There is a particular kind of humility that comes from spending time with the ocean's mysteries. Not the humility of defeat, but the humility of scale. The ocean is bigger than us, older than us, more complex than us. It was here before the first human being stood upright, and it will be here long after the last one is gone. Whatever we build on its shores, whatever we sail across its surface, whatever we dump into its water or pull from its floor, the ocean will absorb it, transform it, and continue. It does not need us. We, on the other hand, need it desperately. Every breath we take contains oxygen produced by marine phytoplankton. Every weather pattern that governs our lives is shaped by ocean currents and ocean temperatures. The water cycle that fills our rivers and waters our crops is driven by evaporation from the ocean surface. The climate stability that has allowed human civilization to develop over the last 10,000 years is maintained, in large part, by the ocean's ability to absorb and redistribute heat. We are, whether we think about it or not, an ocean species. Our lives are governed by the water, and our future depends on its health. The mysteries we have explored tonight are not just entertaining stories. They are windows into the functioning of a system that sustains all life on this planet. The ghost ships remind us of the ocean's indifference. The deep-sea creatures remind us of its creativity. The dead zones and the garbage patches remind us of our impact. And the unmapped seafloor, the unexplored pelagic zone, the unidentified species, and the unanswered questions remind us of how much we have left to learn. If you have been here for all of it, through the ghost ships and the giant squid, the bioluminescent bacteria and the underwater waterfalls, the sounds of the deep and the silence of the abyss, then you already know what the ocean has been trying to tell us all along. There is more down there. There has always been more. And the deeper we look, the more we find that the ocean is not just hiding its secrets. It is inviting us to come and find them. We have covered 70% of the world tonight, and we have barely scratched the surface. If you want to keep diving into mysteries like these, make sure you are subscribed, because we go deep every single week, Drop a comment and tell us which mystery stayed with you the longest, which one kept you thinking after the lights went out. We read every single one, and we will be down there in the comments picking our favourite theories. Click the video on your screen for another deep dive, and as always, stay curious. The ocean is listening. There is a layer of the ocean that most people have never heard of, and that no sunlight has ever touched. Below the sunlit surface, below the twilight zone where the last traces of blue light fade to black, there exists a realm so vast and so dark that the creatures living in it have never experienced a single photon from the sun. Scientists call it the Bathypelagic Zone. Sailors and poets know it by another name, the Midnight Zone. The Midnight Zone begins at a depth of roughly 1,000 meters, about 3,300 feet, and extends downward to 4,000 meters, about 13,100 feet. It is the largest layer of the ocean by volume, encompassing more water than every other ocean zone combined. The temperature is a constant 1 to 4 degrees Celsius, barely above freezing. The pressure ranges from 100 to 400 atmospheres, enough to crush most human-made structures, and the darkness is total. Not the darkness of a cloudy night or a lightless room, where the human eye can gradually adapt and begin to perceive shapes. This is a darkness that contains no light of any kind, a blackness so absolute that the concept of vision, as surface creatures understand it, is meaningless. And yet this is not an empty place. The Midnight Zone is home to an astonishing diversity of life, most of it bizarre by any surface standard. Anglerfish drift through the blackness with bioluminescent lures dangling from their foreheads, glowing pinpoints of light in the void designed to attract prey. In some species, the male is so small relative to the female that he fuses permanently to her body, his circulatory system merging with hers until he becomes nothing more than a parasitic, reproductive organ attached to her flank. Giant siphonophores, colonial organisms that can reach lengths of over 40 meters, longer than a blue whale, drift in translucent chains through the water column, each individual in the colony performing a specialized function, feeding, stinging, reproducing, or propelling the whole assemblage forward. Vampire squid, despite their menacing name, are gentle scavengers that feed on particles of dead organic matter drifting down from above, collecting the falling detritus with long sticky filaments that they extend into the water like fishing lines. The food supply in the Midnight Zone is almost entirely dependent on what falls from the surface. Dead plankton, fecal pellets, shed skin, and the occasional carcass of a larger animal drift downward in a slow, continuous shower that marine scientists call marine snow. The particles are so small and so sparse that the organisms of the Midnight Zone have evolved extreme strategies for making the most of every calorie. Metabolisms are slow to the minimum necessary for survival. Growth rates are glacial. Many species have expandable stomachs that allow them to consume prey larger than themselves on the rare occasions when a meal presents itself. Others have evolved enormous mouths and extensible jaws, ready to engulf anything edible that comes within reach. The Midnight Zone is also a place of sound. With vision useless, many deep-water species rely on mechanoreception, the ability to detect vibrations and pressure changes in the surrounding water, to navigate and hunt. Some produce their own sounds, using swim bladders, muscle contractions, or bioluminescent flashes to communicate with others of their kind across the black distances. The acoustic environment of the deep ocean is rich and complex, a landscape of sound that we are only beginning to map and interpret. What is perhaps most remarkable about the Midnight Zone is not any single species or any single phenomenon, but the sheer scale of what we do not know about it. Estimates suggest that less than 5% of the Midnight Zone has been directly observed by humans, whether by crude submersible, remotely operated vehicle or camera. The rest is inferred from the fragmentary evidence brought up by nets, sound recordings, and the occasional specimen that washes ashore or turns up in the stomach of a predator. For all practical purposes, the largest habitat on Earth is a blank page. Every expedition that descends into the Midnight Zone returns with surprises, new species, unexpected behaviours, organisms that defy classification. In 2020, a deep-sea survey in the Monterey Canyon off the coast of California documented a Siphon 04 measuring 47 metres in length, the longest animal ever recorded, drifting in a slow, spiralling orbit through the water at a depth of 630 metres. The creature was alive, intact, and had never been seen before. It had been there, presumably for its entire life, in water that humans had sailed over for centuries, and no one had known. The midnight zone is the ocean's greatest blind spot. It is the space between the surface we travel and the floor we are slowly learning to map. It holds more water, more life, and more unanswered questions than any other environment on the planet, and it sits directly beneath every ship, every boat and every swimmer on Earth, separated from us by nothing but depth and darkness. We do not need to travel to another planet to find alien life. We do not need a spacecraft or a warp drive or a telescope pointed at a distant star. The most alien ecosystem on Earth is right here, right below us, in the cold, black, pressurized water of the midnight zone, and we have barely begun to explore it. This is the truth that every ocean mystery ultimately points toward. Not that the sea is dangerous, though it is. Not that it is beautiful, though it is that too, but that it is vast, and that vastness is not a metaphor. It is a measurable, quantifiable, staggering fact. The ocean is the majority of the planet's surface, the majority of its habitable volume, and the majority of its biological diversity, and the majority of that majority is unknown. We have been staring at the ocean for as long as we have been human. We have given it names and gods and stories. We have built ships to cross it, and machines to probe it, and instruments to listen to it. We have mapped its coastlines, charted its currents, measured its tides, and catalogued thousands of its species. And after all of that effort, across all of those centuries, we have seen only a fraction of what it contains. The rest is down there in the dark, where it has always been, waiting